Recording. There we go. Hello everyone and welcome to Handmade Hero, the show where we code a complete professional quality game from scratch using nothing, no libraries, no engines, just so we can learn about absolutely everything that's in a game, everything that happens all the way right down to what like GPUs do and stuff like that. So we're actually going to implement absolutely everything, including our own software renderer, so we can see how absolutely everything works and really gain that understanding that's necessary in order to be able to, basically be someone who can build their own engines, build their own libraries if they want to, but also if you're using stuff like that, you'll know exactly what they are doing underneath and how that sort of stuff works. So if you need to drop down and fix something, you can. If you need to make good decisions about what to use or how to use it, you can. You'll basically just have that complete understanding that lets you be like a really effective game programmer at every level that you choose to go to. So that is what we have been doing. We are almost done fussing with the Win32 side of things. We have basically been working towards, excuse me, we've been 20 days into it, which is basically 20 hours into development. We've been building our own Win32 platform layer that allows us to do things like play sounds and render graphics and get input from the gamepad and the keyboard, allocate memory, take timing results. And we've done a tremendous amount of stuff in 20 days actually, and we've done it all by hand. So it's going actually quite well, and I'm delighted about it. Yesterday, unfortunately, we found out that the sound card in this machine is pretty latent. It takes about 33 milliseconds to get sound from when we output it to when it comes out, is the best that seems like we can do. So that's kind of a little rough, but today we're going to, basically go back in there and hit that and see what we can do, try to make it, try to get as far as we can towards getting our audio down to where we want it to be before we move on to other stuff. Anyway, if you have gone to handmadehero.org and pre-ordered the game using this little handy-dandy button, you got a link in your email that lets you go ahead and download Handmade Hero, the source code. Every night I update it so you can always follow along. If you're following along at home, this is day 20, so when you download the source code, there'll actually be zips in there, one for each day. You just unzip day 19, and you will be exactly at the same state that I am when I start today. So you can follow along at home exactly whenever you watch this video, even if you watch it many days down the road. Now, I also believe I changed this from saying weekly builds to all builds. There we go. Because some people were getting confused since it's actually nightly that you can download the stuff. So I changed it to all builds because you get access to absolutely everything every time I push something, and we push something basically every night. All right. That said, let us go and get started here. Someone on the chat was mentioning that we had an off by one error. Now we probably have a couple of bugs in what we were writing yesterday because we didn't really finish. We didn't get to the point where we really actually finished it up. We only just barely threw it in there. We threw in some rendering code. They were saying there was an off by one error with the debug time marker. I'm not sure exactly what they meant by that actually on the chat. If they want to go ahead and point out exactly what it actually is, then we can go ahead and look at it explicitly. But I'll take a quick look just to see if I see what they were talking about. We have debug time marker here. We advance it. I don't see an off by one error in the recording of it. It looks like it's going to record one each time, so that's good. Basically, we go in here, we use whatever the current value of debug time marker index is, we increment it by 1, which is fine in the case where we hit the array. There we go. That's what we were looking for. This should actually be like that. That actually needs to be checking for whether we hit the actual end of the array. So that was a bug. Thank you for that. That is, again, one of those nasty little things. I don't usually make mistakes like that. I have to think that probably it is. I will admit my programming does degrade when I have to talk and explain stuff as we go. I think it takes up part of my brain, and it's a little harder for me to write bug-free code, which at the end of the day is okay because I suspect a lot of people watching this stream are beginner C programmers or intermediate C programmers perhaps, and so possibly it's better for me to have to debug more stuff just so we can go through it. So let's see there. That would lead to a gap once in a while, but we weren't seeing too many gaps before. So it's looking pretty stable here anyway. This is roughly what we were expecting to see before, so we're good. Yeah, so that is all good for now. Basically, what we need to do today is just decide how we're going to handle what decisions we're going to make based on the audio latency. So I'm going to go to the diagram for a minute and just talk about what we basically found yesterday. I should probably double mention, I guess, perhaps what that bug was, just in case people weren't clear. So before, I accidentally had typed that whenever the debug time marker index is greater than the array count. And basically what happens is, remember, these are zero-based arrays. So if I have an array, so if I've got debug time markers and I refer to the 0th element, that's the first entry in it. Because essentially what the syntax means in C, and also it gets translated down to assembly relatively directly. Basically what this means is I'm going to take the pointer to the beginning of the array, which is debug time markers, and I'm going to add 0 to it, right? So what that means is the first one is actually 0. And the last one is actually whatever the count is minus 1, right? Because if we actually added all the count to it, we would be past the last one. We'd be pointing to one past the last one. We'd be actually pointing to one byte after the very last byte that was reserved for this array. What that means is that when we get to the end, we're actually at array count when we get to the end. I don't really need this greater than here. It's not really necessary. Really what we're talking about is when it's equal to array count. That's just kind of being paranoid and saying, well, if someone came in here and mucked with this value in some really bad way. But of course, we'd still have a bug even if that happened. So really we can do this. And what we probably should do is say this. We should probably say, let's assert that we're never going to access outside that array here, just so we can double check and make sure that we don't. So that's really all we're talking about. Nothing really too bizarre. But anyway, so that was just a stupid bug, and now it is fixed. And we can take a look a little bit more. Okay. So I'm going to go ahead and open up the infamous Microsoft Paint, Paint Program of Champions. And we're going to talk a little bit about what we learned yesterday, much to our chagrin, I should say. So we decided basically to start off with trying to hit 30 frames a second, right? And 30 frames a second translates into, right, you've got 1,000 milliseconds per frame in one frame, right? That makes sense. And so if we're doing 30 frames per second, 30 frames per second, right? Basically what we're expecting here is if we actually want to know how many milliseconds we're actually going to have in every frame, we would divide by 30, right? And so what ends up happening is we're expecting to see about 33.3 milliseconds every frame. That's how long we expect this to take, 33.3 milliseconds, like that, if that makes sense. Unfortunately for us, what we end up with is we end up with a we have a sound card in the machine that's going to output our audio, and what we would like to be able to do is we'd like to be able to output the audio and the video synchronously. So what we'd like to be able to do is inside any given frame boundary, we're computing the next frame. So if we are in here, if we're somewhere in here, you know, basically we're showing some frame, and this is the next frame. Basically, we're computing a graphic, right? You know, we're computing a little graphic here. We're trying to compute something that we're going to show right at this boundary. So this is where we're going to start displaying this to the monitor. So we're computing it, you know, sometime in here, and we're going to try and show it here. So ideally, what we would like to do is also compute the sound that goes with this frame and have it line up exactly. That's what we would like to do. Unfortunately, what we found out is that the audio latency on this particular computer anyway, it obviously is going to vary when going through direct sound. And we don't know, it might be lower if we were to try X audio. We haven't tried that yet, but you know, we have no way of knowing until we actually try. Basically, the audio latency is on the order of 33 milliseconds itself. We took a look at the difference between what's called the play cursor and the write cursor in direct sound, and we found that basically we could expect somewhere around that 30 milliseconds of latency, which is our entire frame time, which means that assuming we're inside a frame and we're displaying something and we're computing the next one, we can't expect our audio to show up until somewhere like in here, basically. Somewhere that's like wherever we start writing it. If we write the audio here, we couldn't expect it reasonably to show up at the earliest until somewhere out here, which means there's no way for us to actually compute the audio that goes with a particular frame and actually have it show up on that frame. That's just, there's really nothing we can do about it. That's just the truth. So, we've got a couple options here, and I can tell you about what they are, but none of them are great. What we may have to do is just regress to a very basic sound loop and just accept the latency and accept that it's never going to be synchronized, or we can try to do something that is synchronized on a machine that's faster, and we'll just test it somewhere there. And I don't mean faster like CPU, I mean less audio latency. But basically, if you think about what happens inside of a frame, we do have some other options that we could try to pursue, and I'll just discuss what they are briefly, and it may lead to us changing the way we do audio in our platform layer just a little bit. So basically what happens is, if we break down the time, there's inside of a given frame, let's say we're taking this frame, and we want to kind of blow this out into what is actually happening inside the frame. So we're going to divide up this time. This is our 33 milliseconds. We're going to divide up this time into what we're actually doing, right? What we're actually trying to do. What we're going to do here is the first thing we're going to do that doesn't really take a lot of time is we're going to gather input, right? We're going to gather input, okay? So we're going to get the keyboard, we're going to get the mouse if we wanted it. We're not really using that in the game, but we may use it for debug purposes. We're going to get the keyboard, which we are using for game pads, that sort of stuff. We're then going to update the game, right? So that's this. We then have some amount of time that we have to do update the game and make a render list. So we have to update and like do render prep, basically, right? And you'll see what that is kind of as we go through. But we're going to update and do render prep in here, right? Then we're going to actually have to do rendering, which is the majority, especially in this type of game where our physics, we're not doing like a 3D game, so our full 3D physics and collision detection, that sort of stuff, would normally take more time. But since it's a 2D game, we'll probably be able to keep that code pretty optimal when if we write it properly. So we're not expecting this to grow that huge. It'll be complex because I'd like to make it fairly complicated, but I don't know that it'll grow that huge. It might if we start doing some things like fluid effects and stuff like that. So we can't guarantee that, but chances are, especially when we have the software renderer, this is going to be a huge amount of time. When we start using GPU, it might go down quite a bit because GPUs, especially if it's a fast GPU, will just romp through a 2D game. But you never know. We can run in 1920 by 1080 all the time, and at full multi-sample and stuff, and suck down more GPU time and stuff like that. So you never know. Point being, that takes a bunch of time, and then any time that's left over, we're just waiting, right? We're just going to wait until the flip, right? And then here we actually display the frame, right? And this can actually be pipelined to some degree. So depending on how deep the pipeline is, a pipeline is basically something where you're going to push more frames down, have frames be computed overlapped. So we could start right after we finish rendering this, or even if we were multi-threaded, we could start doing gather input and updating before we even do the rendering, right? There's a bunch of ways we could overlap this. But if we're just doing it synchronously on one processor, no overlap, then this is what that's going to look like, and then we flip, right? And certainly back in the old days, this is what it looked like because there weren't multi-core things, there wasn't a GPU, so you were just talking about this exact process: gather input, update, render, wait, flip, right? Now the question then is, where do we insert sound in all of this, right? The answer obviously would be, if we are trying to minimize our audio latency and hit this time right here, then if we have a 33 millisecond sound delay, if we have something that's close to the frame thing, then we'd actually have to start outputting the sound for the next frame. We'd have to output it like back here, right? Does that make sense? We'd actually have to output the sound before we even gather the input for this frame, which means that it's sort of somewhat impossible for us to do. But if you think about what was actually happening, if we go ahead and tack on basically another frame to it and look at the same thing, so basically just copy what we just drew, over here, what was this period back here that was before the thing? Well, this was the wait period, right? And then before that was the rendering period, right? So actually, all the way back to almost the beginning of this other frame, like let's say this right here is only taking 10 milliseconds, and this right here was taking 23 milliseconds, right? So we divide the frame time up, and basically the gather input and that update step is maybe only 10 milliseconds, and then we spent a lot of time rendering and waiting, probably mostly rendering. Well, that means all the way back here, if we look at what the time was, right when we actually, after we did the update, where we could have known what the sound was going to be, right, for the next frame. If we go all the way back here and look at that, if we were to sort of output the sound right here, on the previous frame, we could have been only one frame behind, right? If we did everything exactly right, we could have been only one frame behind. And furthermore, if we actually take this wait period, or if we take this render period and overlapped and started the update for the next frame here, right? So this is where the gather input happens. So we basically overlap the gather input and update for the next frame with the rendering of the previous frame. If we actually overlapped those on 2 cores, we could actually hit the constraint of being 40 milliseconds or something ahead of where we wanted to write that audio and actually get our audio synced. But there's a cost. The cost is now we have pushed input gathering back a little bit further. So we've introduced basically 23 milliseconds, somewhere around, at maximum, 23 milliseconds of input lag, right? That would be the cost. So if you think about that, is that a good trade? Probably not. For a game like this one's, audio sync is not that important because none of the gameplay really revolves around hitting a sound directly. We will probably have audio cues in the game that try to help the player understand what's going on, recharge times, whatever, enemy attacks, that sort of thing. So, audio is important in every game. I certainly don't want to suggest that it isn't, because it very much is. But how tightly the audio sync is as a priority versus how tightly the input is synced, in this game, I'm going to say that the input lag would be way worse if we did that. So I think we really want to push our gather input as far forwards as we can, and we don't want to introduce that extra lag. So, given that we don't really have any options, realistically, given that, for hitting our audio sync on a given frame, what I'm going to suggest is that I backpedal a little bit from what I was hoping to do, which is keep the audio and video synced to frames, and basically say, all right, we're going to fall back to a little bit stupider, right? And what we're going to do is just say, all right, we're computing our stuff, and somewhere in here, after the update and input has happened, somewhere in here, we're going to try to write the audio. And we're just going to accept the fact that it's not going to be on a frame boundary. It's going to be basically somewhere in the middle of next frame. And we're going to accept the fact that there's basically 15 milliseconds or so on this card of audio latency, and it's going to write right into the middle. We will lie to the game. So we will tell the game that it is outputting this frame's audio. So the game doesn't have to try and account for that 15 milliseconds of lag. We won't complicate the game's code by forcing it to do that. But what we will do is we'll basically say, all right, you go ahead and output for the frame. You're actually going to be lagged by a little bit, and this is kind of a very standard audio loop, and it's unsynchronized. It's a bit sloppy, but it's better than the alternative, which is pushing it out to this frame and having one whole frame of lag, or buffering a whole frame ahead and introducing input lag. So what I'm going to try to do is basically write it, go change our audio code so that is what we do in the case where the audio latency is greater than what we think we can achieve. In the case where it was less, like let's say we look and the audio card's got like 5 milliseconds of latency. It's like awesome. Maybe we're on a console or something and we can get that. Then what we will do in that case is we will try to make it so that it is offset, and basically we will write the audio with some buffer so that the audio for a frame does line up with the frame. So basically, we're going to have basically a conditional sort of output. There will basically be one path for latent and one path for non-latent audio. And they won't really be paths, they'll just be our computation about where we're trying to hit will basically be sort of thresholded. So when we look at that lag, assuming that it's more than the some conservative estimate about where we can update our audio. Let's say that we assume that we're going to be able to update our audio, 16 milliseconds into the frame or something halfway through. Then we're going to say, well, if that difference here, if the audio latency is 16 milliseconds or more, then we're basically going to have to just be writing as soon as we can. If it's less than that, let's push it up to that 16 milliseconds to try and keep it right about here. And we can even measure what our average update time is in here to try and keep that as close as possible, if that makes sense. So yeah, we can do a bunch of stuff like that to try. We'll try to do the best we can, and we'll go from there. So that's about all we've got, and I'm going to go ahead and do that. I think I mentioned on Twitter, for those of you who are following, I feel like today might be a long session. I'm going to go ahead and do this. It'll take us a little while to do because this kind of code is always very finicky, very error prone. You saw how many mistakes I already made in it. And we'll make more, I'm sure. So it's going to take us a while to kind of go through that. But if we finish that in a reasonable amount of time, I may double the length of this stream and basically do 2 hours plus the Q&A instead of 1 hour plus the Q&A, because there's some other stuff that I might want to do, and I feel like it's a Friday, it's the middle of the day, I don't have any particular time constraints, so I might just do a stream that's a little longer. We'll see. We will see where we get. Alrighty. So basically what we've got here is we have said that we're going to have frames of audio latency, and I'm basically going to get rid of that notion altogether. So I'm going to get rid of frames of audio latency. We've got a monitor refresh rate. We've got our game update hertz here. And basically what we're going to do eventually is change these into, let's take a look at these. We've got our two to-dos here. What we want to do eventually is change those to run, to query Windows for the refresh rate, which we think we can sort of do, and just assume 60 in the case where we don't get it. But anyway, so what we're going to do here is actually delete this to-do that says let's think about running non-frame context for audio latency. That is what I just said we will decide to do. And let's use the right cursor delta for the play cursor just to target audio latency. That is also what we are going to do. So basically what we're going to do is every time we take a look at our get current position, right? So we come in here and we take a look at get current position. The play cursor and the right cursor, the difference between those two things is sort of the minimum audio latency we could ever expect to have, right? The right cursor says where it's safe for us to write to right now. The play cursor says where the audio is playing as far as we know. So if we look at those two, the number of samples in between them is the lowest audio latency we can realistically expect to count on direct sound giving us in terms of what it's actually playing, right? So we've sort of got a value here, right? We've got a right cursor minus play cursor. Excuse me. We've got a value here, which is basically bytes between, where we're going to do right cursor minus play cursor, and that will sort of give us what we expect our delta to be. Now we've got a problem, which is that again this is a circular buffer, right? So since this is a circular buffer, whenever right cursor actually happens to be ahead of play cursor in the buffer, this would work. But unfortunately, if the right cursor actually happens to be behind the play cursor, that means that the right cursor has wrapped around the buffer and come back to the beginning, but the play cursor hasn't yet. Then this would not be correct, right? So what we need to do is we need to account for that and kind of say the bytes between cursors is going to have an if in it, right? It's going to be one or the other of these two things, and we have to compute them separately. So basically what we have to say, well, actually, we don't even have to really do it that way. We can be a little fancier. So we can do something like dword unwrapped right cursor, if you will, we can basically say that the unwrapped right cursor is equal to the right cursor, but if for some reason the right cursor is less than the play cursor, right, then we just do and I'll just say unwrapped here, then we just add the size of the buffer in. So buffer sound, let's sound buffer. There's some parameter we did that was like the total size, right? So basically all I'm saying here is like, okay, we'll get the right cursor. We know that we can just subtract wherever the right cursor is from the play cursor because it's always going to be after it. But in the case where the right cursor has wrapped around so that it's now before the play cursor technically, we'll just add in the buffer size, which is where it would be if the buffer wasn't circular, right? And we'll subtract those two, and that should always give us a constant value. And so that's going to be basically a delta. That's going to be our latency, essentially, our latency in bytes. So bytes between cursors, right there. I'm going to go ahead and compute that and just guarantee that that's true. We're going to go ahead and change this value in a second. So the latency sample count, we're going to go ahead and neuter. So in a second here, we're going to say get rid of latency sample count because we are not going to use that anymore. And what did I do here? Is not a member of game. Oh, right. Well, where's our? We need our actual sound output buffer. There we go. Too many names for too many buffers. And so I just want to take a look at that for a second. There we go. I want to take a look at that, and here's our delta. So that's looking nice and stable. You can kind of see even we can spot check the case that I was concerned about. We can see the play cursor and the right cursor. Here's the case that I was trying to handle. The right cursor is behind the play cursor here. So if we had subtracted these, we would have gotten a number that we were unhappy with. So basically we've fixed that. And we're constantly computing the delta between them. Now that 5760 number, that is essentially our audio latency in bytes. There we go. We are basically computing our audio latency in bytes there, and that is all we needed to compute. Now there's a variety of ways we could have computed that. That's just the one that I thought was the most easy to understand, the easiest to look at the code, so I think that's a good one. And from there, we should now be able to say that value in terms of samples, that's sort of going to tell us basically a number we can use to reason about our audio latency. So in some sense, you could think of we now have our audio latency seconds, right, is going to be however many bytes there were between cursors, that's the bytes, divided by the bytes per sample is how many samples, right? How many samples there are in our audio latency, right? How many samples of audio latency. We also have our samples per second, right? And our samples per second basically is a divisor that tells us if we take samples and divide by samples per second, we're going to end up with seconds, which is exactly what we want. Again, dimensional analysis. You always want to think about that for a second. If you know what I'm talking about, basically this is that dimensional analysis coming in again. I do it in my head a lot, so it's hard for me to always remember that everyone might not be familiar with it. But if you look at what we did there, we're basically saying bytes between cursors. So we basically have a value that's in bytes, right? First, so that's this value right here, bytes between cursors. We're dividing by sound output bytes per sample, right? So bytes per sample, we're dividing by bytes per sample. And dividing by something over something else is the same as multiplying by swapping those two, right? So we're dividing because we basically want to multiply by, instead of bytes per sample, we want to multiply by sample over bytes, right? That cancels the bytes value and leaves us with samples, which is what we want in the top. We then are dividing by samples, right, per second. And again, that just swaps these two. So that's seconds over samples, right? And this becomes a multiply, right? That swaps those two. Cross out the samples, and we're just left with seconds, right? And seconds is what we were trying to compute. So again, just dimensional analysis, really simple. It's a way to work out the ratios in your head until you just do them by rote, which I tend to do. So anyway, that's all that is, right? So bytes between cursors divided by bytes per sample is the number of actual samples, and then divided by the samples per second. We could also have, if we wanted to save ourselves some time, we could have put bytes per second in there, which is probably a good idea. In fact, maybe when we're doing some cleanup here, to do, Casey, math gets simpler if we add a bytes per second field, because we could just use that, which has this sort of baked into it. So anyway, something to think about. But that will basically give us our latency in float, but remember, it won't know to convert to float. It'll look at all these. It'll look at these three, C will, and say they're all integer. So this would do the divide in integer. Now that first divide we can do integer divide if we wanted to, because it's going to be an even multiple. Bytes between cursors is an even multiple. But I don't really need it to do that. I'm gonna tell it to do everything in float anyway. So I'm just gonna cast those up to floats because we want the final thing in floats. So at that point, we actually do have our value in seconds, so I could print out that as well, what the delta is in seconds, and just, why not, audio latency seconds, just to make sure. You can never really be too sure. With the number of crazy things that happens in programming, you can never be too sure. And so there you go. You can see that that's exactly the number that we were suspecting, right around 33 milliseconds, which is what that number is. So we're basically looking at 30 milliseconds, slightly less than the frame time, is what we've got. So that is our audio latency seconds. That is the best that we're ever going to be able to do. So looking at that value, basically what we want to say is when we do our computation of what to write, we're going to take a look at this audio latency seconds value, and our in fact bytes between cursors. This should be audio latency bytes, really, right? So audio latency bytes, and that basically is going to be right here. So what I'm going to do is I'm just going to save these values for now. These are going to be actual values that go with our sound is valid thing, and maybe now might be a good time to start pulling these out, but I'm basically going to put those in there like that. Audio latency seconds, where's audio latency seconds? There we go. So I'm going to compute those so that we can basically use those later when the sound is valid and we're computing where we're going to write to. Because you remember we kind of did a thing where we said that we wanted to make the sound be valid sort of the next time around. So here's our sound is valid. Again, bytes between cursors, audio latency bytes. There we go. All right. So basically that's just going to leave those values up here for us to be able to reason about when we go to actually output the sound. So let's take a look here at where that happens. So that happens right here. Basically what we were doing is we're computing where we want to generally end up in terms of where to write to. Where sort of in the running sample index we want to write to. So we know that we've set our running sample index. If we look when we first start up, we're going to set that to be equal to wherever the right cursor was. That is where our running sample index is. And I'd also say for math purposes to do should running sample index be in bytes as well, because a lot of times we're mapping in and out of samples, but I wonder if that's really all that useful, because remember the running sample index is really only used up here for this particular thing, and we could just go ahead and keep that in bytes, which might be a little smarter, save some math, and possibly reduce some errors. So that's all we're doing there. We're basically saying we're going to write, this is the last place we wrote to, and we now need to know, since we're going to lock from there, where is our target cursor, right? Where is that actually going to be at? And so before we were using the last play cursor, but now I think probably what we want to do is we want to basically say whatever the last right cursor was. So the last play cursor will actually keep the last right cursor as well. Let's see here. And this should make some people happy because they were nervous about the way I was doing it before. And they're right to be nervous. It's always good to be nervous. I'm an experimenty kind of dude. I go in to code oftentimes. Oops, why did I delete that? I just wanted to add this one. I didn't want to delete the other one. I'm just going to save both of them here so we can take a look at both of them when we're doing our computation and printouts and so on. I like to go in and you can tell this code is very fluid, right? I'm just kind of hacking this stuff in here as I experiment around with it. And then you'll notice I've also never decided to pull this code out and tried to clean it up into a little encapsulated thing. And the reason for that is it's just not right yet. Like, we're playing with it. I'm not happy with it. I tend not to pull stuff out until I'm happy with how it works. And that is what's going on here, right? I'm just basically in there mucking with the code, trying to see what seems like a good way to have it work. And that's a very intentional. That's a very specific way that I tend to program, and I think it's a good way to program. Basically, I think that it's important not to try to make good, clean, readable, lovely code right away, because you burn a lot of time when you're in this state like we are now, where we're kind of pushing things around, where things are kind of fungible, and we're trying to massage them into a place that we're happy with it. We don't know very much about the hardware. We learned a lot about the hardware yesterday, all that sort of stuff. And so we're kind of pushing towards that point, and while we're in that state, I like to kind of keep things pretty sort of messy and fluid. I find it saves more time in the long run to do it that way. You don't want it too horrible, because you don't want to introduce bugs by how horrible it is. So we want to try and keep it a little bit cleaner, but, you know, we do what we can. Plus, I gotta admit, I can cheat a little bit, because on this stream, there are so many people who watch this program. I get kind of lucky. They catch errors for me, too. So I get a bonus. It's almost like I've got a pair programmer with me programming all the time, catching stupid mistakes that I make. That's kind of awesome. You gotta admit, there's some fringe benefits to doing this stream to me. It's actually kind of pays off a little bit, just in terms of extra eyes on the problem. And you would be surprised how much that helps, because when you're programming, you miss stuff all the time, and having people who are just doing nothing but taking a look at your code and going, hey, wait a minute, does that work? And then going, he missed something, is pretty great. It's like having a whole suite of pair programmers standing behind you, just like catching problems. All right, so anyway, we've got those values now. So what we need to do is we need to think about when we're going to do our computation of where we want to write to. Basically, we know what our audio latency is. We know what the write cursor was, right? And so really all we have to determine is how much past the write cursor we actually want to write in terms of the sample count. So basically what's going to happen here, going back to the diagram, is we're in a situation where we've just flipped, right? We just flipped, and when we did the flip, we're at this point in time. In fact, you know, I can show you where we are in the code when this happens, right? We did our sleep, and by the way, that reminds me, I wanted to change this to this is not really supposed to stay in here. So log miss here. So this should actually not be an assertion, because this will happen. I don't like assertions for things that actually we know are going to happen. So we need to log a miss there. It's not really. This is a missed sleep. Missed sleep here. So okay, sorry about that. Just needed. I remember things sometimes when I'm thinking about them. I remember things, and I'm like, I wanted to change that, because I don't ever like asserting things that are actually going to happen. That's fine. I assert things that are going to happen when I'm testing code, but I don't like to leave those in there. The game should never assert when you're running it. That's always just a bad thing. All right, so basically what's going to happen is right here, we did our flip, Win32 display buffer window, and then we asked what the current position was. So basically we did our flip here, we asked what the current position was, and we kind of know that the play cursor is going to be like, so we're right here, we're here, right at the flip time. We asked where the play cursor is, and we kind of know on this machine it's going to be like right there, right? It's going to be pretty darn close to where we were, at least what we're expecting, right? And so the right cursor is actually going to be, let's see here. The right cursor is actually going to be somewhere out in the, the frame like here. This is where the right cursor is going to be, if that makes sense. Now it could really be anywhere. I mean, we don't know that. I'm just saying, the play cursor is going to be somewhere behind where we are in theory, or close to. If we were really good, it'd be close to where we are. Or I guess you could even think of it as the play cursor might even be in front of us. So it's going to be somewhere right around where we are. Hopefully, if our audio sync isn't awful, it's going to be somewhere in here. Then we basically got the right cursor, and the right cursor could be anywhere out here, right? So we're hoping that the right cursor is somewhere kind of back in here if possible. We're hoping that we're not a whole frame ahead, but whatever, it's going to be somewhere. So then what we have to determine, right, is from that right cursor, how much do we have to write ahead in order to make it so that the next time that we come back around, our audio latency hasn't caught up with us, right? So we're going to do a write, and we know we're going to wait 33 milliseconds. So we have to do at least 33 milliseconds worth of writing, because we know that however far, whatever our sync was, we're going to basically have to try to do roughly 33 milliseconds of writing. But we also need to account, and if these clocks were perfectly in sync, it would always be that 33 milliseconds of writing that we want after the write cursor. But we also have to figure, well, we've got this audio latency in here to account for. Now, I guess if you think about it, if the audio latency, this is the part that I was talking about with the two conditions, if we know that the audio latency is larger than the frame, so basically, I kind of need a better diagram here because this stuff is kind of confusing, and I want to make sure that I've drawn it out just right. Okay. So let's take a look at that very first frame. All right, so we basically have our thing going on here. We're going to do our first frame is silent, basically, because we're not actually displaying anything. Our first frame is silent. We go to do the flip. This is the first time anything actually shows up on the screen. So we flip here, and then we ask, essentially we've got our sound buffer. Our sound buffer is here. This is our sound buffer right here. We ask where things are, and we find out that the play cursor is here. We find out that the right cursor is somewhere around here. So there's the play cursor and the right cursor. We figured this out at this particular flip, right? So that's where that is. Now, basically what we have to do is we have to start writing to here. This is where we're actually going to write. And so how much sound are we actually going to want to write? Well, it seems like we just want to write, at that point, we definitely would just want to write 1 frame's worth, because we know that this is already accounted for. So the play cursor is going to have to go the distance of the audio latency, which is our actual latency, right? It's going to have to go the distance of our audio latency and then start playing, and it's got a full 33 milliseconds to go, right? So that's totally what we want. And then this is just our 30 milliseconds of audio latency that there's really not much we can do anything about. Now, if we wanted to, then this is where it gets even hairier, right? You could imagine us actually waiting on that. We could, or doing that guess right about here, the first time out. We could imagine doing that guess right about here, and that would reduce our initial audio latency, right? If we asked here instead of at the flip. So what we could consider doing is saying, well, yeah, let's move it back instead of doing it the way we are. Let's say we asked for it here, right? Then we know that we basically are going to wait this amount of time. So there's however much time between when we ask and when we expect to do the flip, right? That's going to be the elapsed time here, right? And the total time here of the frame, the total frame time. It's going to be the difference between those. It's going to be total minus elapsed is this time, right? So our total minus elapsed time is how much of the play cursor, right cursor thing we expect to eat up before we actually start playing, right? If that makes sense. So we kind of could query that here, go where is the soonest we could write to, if that number is less than this time, if this difference between the right cursor and the play cursor is less than this time, right? Then we are at that point. Then we are at the point where we need to delay and push it out further. So we're going to write after the right cursor, basically, right? And line it up like that. If it's later than, we're just going to write at the right cursor, and we're going to write that 33 milliseconds, right? So that's kind of complicated to think about. I'm complicating it even myself. In my head, I'm like, oh man, this is kind of complicated. So basically what we're doing here is whether that audio latency threshold is hit or not, we're going to have to do a different sort of thing. We're either going to have to intentionally sort of push our audio out in the case where we have a super fast sound card, or we're going to have to just write directly to the audio right cursor. when we look at where the right cursor actually is, we're going to write 33 milliseconds out from it in the case where it is too latent, right? But so thinking about this a little bit further, basically, I think that's all it boils down to. So we look at the right, I think, even though it's very complicated to think about, it's a lot of mental gyrations here, I think all that means is what we should do is when we go to write to the audio, we look at where the right cursor is, we say that we need to be ahead of that right cursor by the frame time. So we're going to write 1 frame's worth of audio past the right cursor. But in the case where the right cursor is actually far enough ahead that we don't expect to get there in time, we write that much less audio, right? So basically, if we go ahead and we query these things, and the right cursor is actually inside our frame boundary, it's actually earlier, right? The right cursor is somewhere inside before where the flip is. Then when we write the audio out, instead of writing the full 33 milliseconds, we could decide essentially to kind of push that out a little. How would that work exactly? The first time through, we would add a little bit of time to it. See, the confusing thing is we always have to write from where we left off. So the next time, I'm going to have to actually do this out just to make sure that we're doing it. I'm going to actually do 2 frames, right? So the first one I'm going to do, I'm going to actually work out the cases 100%, just so I have both a good explanation and in my head a good way. So let's do first, this is audio low latency. So very low latency audio happening here. Something that's going to be extremely low audio latency on the sound card. So we ask here, this is our ask, and it turns out when we look at how much time the audio is going to take, we expect it to basically, the right cursor will be here, right? So what we would want to do there is we'd want to move the right cursor forward on that first frame so that it lines up with this. So we're actually going to start our write here, and we're going to write just 1 frame of audio, right? That's all we're going to write, is 1 frame of audio. So that's what would happen here. We then ask again here, right? And we assume the audio latency is still very low, so we would get the fact that the right cursor is here, and we would be here writing to it, to this frame here, and we would want to write 1 more frame. So in this case, we would basically always just be writing just the 33 milliseconds, and we would never want to write anything else, right? But there's the audio clock problem, where we want to make sure that we're not going to just constantly fill the buffer. Like, let's say we were slightly off, so we were always slightly writing too many bytes because our wall clock and the audio clock diverged. The audio clock was a little slower or something like that. That's the part that makes things really complicated. So we can't always write exactly 33 milliseconds. We have to write 33 milliseconds adjusted by however much the clock consumed. So what we need to see is how far did the right cursor move between those 2 times on average, right? So what we're going to do is say the average, instead of saying 33 milliseconds, we're going to say whatever the average right cursor movement was over, some number of frames, right? So we're basically going to say however much we think 33 milliseconds is in audio clock time, that's how far we would write ahead, right? So hopefully that makes some sense. So when we look at the right cursor, we'd say if it's going to be within here, we'll actually push it out to where we think it should be, and then we'd always write that average every time. That's what we would want to have happen. So basically, just to summarize what would happen here, we're going to, if we're inside frame for the right cursor, then we always write the average right cursor motion amount, right? So that's what we would do here. And I think that gives us the least audio latency versus the frame, because basically the sound would show up early if we just wrote to the right cursor, and we don't actually want that. So we basically want to wait. We want to do on that first one, we want to try to line them up, and then from then on, we always try to want to line them up again. Now, could we do this in a better way? Is there some way to look at the right cursor and do it without having to track that average? Because that would be nice if it was just a more stable computation, if that makes sense. How would we do that? So if we wake up here and we basically find out that the right cursor, the difference between the right cursor and the play cursor is so we would expect the play cursor to be here in all, if we're assuming low latency card, we expect the play cursor to here. We find out that the right cursor is here, so we know the delta between these two is that, and we can sort of say, well, all right, in that case, how far do we want to write? Well, we want to write from the right cursor forwards to our sample index. We're assuming that the sample index fell on a frame boundary. Gosh, can you even do that computation? How would we do this computation using only the right cursor and the play cursor? Because they're the things that are in that clock space. Is there a way to do that? Yeah, I can't think of it. To be honest with you, I can't think of it. We know how far forward the right cursor, we know how far forward our estimated number of samples per frame is, but we don't really know, we don't really know anything else. That's something to think about. I don't know if anyone out there on the stream can think of a better way to do this. It seems pretty tricky to me to do anything other than just track that average, right? To track, you can see what I'm having trouble figuring out if there's a way to do. Basically, this is a wall clock thing that we're doing here. We're using a query performance counter, but the audio clock may not be perfectly synced with the wall clock. It may be like a sample or two off or something, who knows, right? And you can ignore the 5-minute warning. Like I said, long stream today, so we're good to go. Basically, the wall clock, this is what the wall clock is thinking, but the audio clock may be off. So I can't just use the wall clock to determine how much to write. I can't just cold write out the samples. So what I need is a way of saying, if I'm estimating where this is going to be, if I ask and the right cursor's here, the play cursor's back here, and I'm estimating, okay, if the play cursor is here, where is the play cursor going to be when the time has elapsed? I can estimate where the play cursor would be, I can estimate where the right cursor would be, and I can basically say, okay, I'm going to make sure that we write at least past where that right cursor is, at least one frame past it. I guess maybe that's the way to do it. Okay. How about this? Here's a proposal. Here's a proposal for you. Tell me how the stream likes this. Let's say we do a thing where we wake up, we ask where the right cursor is, we forecast forward where we think it will be, right, basically. We say, all right, we have a wall clock estimate for where we think the right cursor will be. We push that forwards. We then say we want to write at least up to the next frame boundary from there, right? And that is the sample index that we write to. So it's always based off this. So in the case where the right cursor, and we do that only when the right cursor is behind, basically, right? Okay, I like that. We basically say round up to frame boundary from where the right cursor is projected, because that basically gives us the thing that we wanted, which is we always just fill the next frame and we're synced. We're synced to it properly at that point if the right cursor always is kind of behind. I like that. I like that a lot. That is feeling much better to me. I think we're getting there, people. Does anyone else love this stuff? That's the weird thing about it too. I feel like there's probably a lot of people watching. God, there's just so much finicky stuff in here, but it's just like there's something so satisfying about banging your head against something for a little while and then making a little breakthrough. It's kind of like playing a great puzzle game, right? It's like it was confusing. it was confusing, right? And then you start to see little sort of breakthroughs there, and we're getting much better than we would have had if we just threw audio out the sound card. If you just throw audio out the sound card, you have no idea how it's synced. So even if someone makes a really low latency sound card and gives you this great hardware, your game just threw it all away. So you weren't synced at all. You now your audio was early instead of late. But if we actually take the time to work this out just this one time, we then have an audio layer that can actually respond to that and be pretty cool. So I think we're making good progress here. And this, I don't know, this is what I like about programming. And then you get to write that great article someday, right? That's like how to do audio output right, and everyone can benefit from it, right? So I feel like it's good. It's just good to work this out. So I feel like that's it. I'm gonna redraw this here and make sure that I think that it's good. So we've got two cases. This is going to be the low latency case, and then we'll work out what the high latency case is in a second. Okay, so basically what happens is we wake up, we need to write audio. So this is our wake up. We find out where the right cursor is. We find out that the right cursor is basically less, we figure that it's inside the frame boundary, right? So the right cursor is inside the frame. That means that we will be able to actually be audio synced. We know that on this, we have a card that is low latency enough that we will be audio synced. So that's a card that had like 10 milliseconds of audio latency, 5 milliseconds of audio latency, some kind of pro-grade audio stuff coming down the pipe here. That's what we got. Maybe you're running on an ASIO driver, it's professional grade, who knows? Or you're on a console and things are direct. So basically what we do in that case, what we do in any case, is first we project the right cursor forwards. So we take the right cursor, right? We take the right cursor plus frames, the frame samples, however many frame samples we want. If that makes sense. So we take the right cursor plus the number of samples per frame. We look at where that is. It's here. We basically say, okay, we're going to want to write up to wherever the frame is. So then our target is basically the next frame, the next expected frame boundary, right? So wherever that's going to be in time, next frame boundary in time. That's where we write to. So we write up to here, right? We come there and we then say, all right, we woke up here. We asked where the right cursor is. It's like here, roughly where we thought it was going to be. We project it forwards. We truncate up. We look upwards. We say that's where it has to be. We write forwards, right? So this is basically what we are trying to do. Okay. Now let's take a look at the case where we have a high latency card. So we wake up here, and here's our frames again, same frames. We wake up here. This is where we wake, right? Same time, because we're basically assuming that the game update's sort of not based on the sound card latency. So we sort of, waking up is a bad term. It sounds like we're sleeping. We get finished with the stuff here. We look at where we need to write our audio. We find out that the right cursor is actually going to be, out here somewhere, right? Excuse me. Okay. The right cursor is going to be out here somewhere. So we're like, yikes. All right, so the right cursor is actually like past where the actual frame boundary is. So we know we're going to be super latent. Basically what that means is that where we need to write to is going to actually be just up to the next frame boundary at all. Is that correct? If the right cursor's there, then the next time we wake would be here. No, so basically it's the exact same. The code is still totally exactly right. The only difference is when we write up here, we could choose not to round up to the next frame boundary. We could choose just to add a different amount in here. So we could add however much we think our audio latency safety margin would be, basically, is what we could do. So we could do this right here. The target is rounded up to the next frame in this case. In the other one, we do the same thing. We do the WC plus frame samples, but instead now the target is just that. The target is that plus a safety margin, right? So we won't round up to the next frame. We'll just have a little safety margin, whatever we think we can get away with there, the lowest thing we think we could get away with in terms of our safety margin. And the safety margin would basically be, I mean, it's basically going to probably be just a few samples. I mean, it's because basically we're writing right where the right cursor tells us to be at that point. So the safety margin could be as little as like 1 millisecond or something, right? I think that would probably be fine. It's however much we think there might be variability in this, if that makes sense. So that safety margin can actually be quite a bit less than the delta that we were pushing up, right? So these are the two things here. So now the only thing we have to deal with is at startup, we don't actually know the concept of where the right cursor is not particularly understandable, right? If that makes sense, because we don't actually know where the right cursor is inside our frame, inside our kind of concept of a frame, if that makes sense. Like saying where the right cursor is versus it, I guess we do. It's just the play cursor is where we are now, right? The play cursor is where we are now, and the right cursor is where we will be. That's like as good as we can sort of do at that first initial startup. Does that make sense? I think that makes sense. So basically, we look at the delta between the right cursor and the play cursor. That's what we're going to get. Now, there's a problem. The thing with that as well, mapping that in there, that makes things even harder. So this seems like the right computation, but the one thing we have to remember is this play counter thing is very latent in terms of how often it updates. If you remember, basically that jump, let's take a look at that for a second here. I left that loop in for a very good reason. That jump that happens, let's see here, turn that back on. So remember, I did a little thing here so we could see how frequently the audio updates at all. Like basically just, you know, just taking a look at what the jump is of these two things. So if I take a look here, that's the bytes, the minimum bytes that it ever goes up by. So 49920 minus 48000, that's how many bytes it goes up by. Divide by that, and we get 480 samples. So again, 480 samples, pretty big. Oops, love that shake thing. I wish it wouldn't do that. I should turn that off. 480 is the granularity of that, of the 480 samples. So 480 samples, if we actually divide that by the total number of samples per second, that's 10 millisecond granularity. So basically what that means, if we go back to the drawing, this is why I'm getting so nervous about this, because this is what we actually want to do if we could map these into time. But if you think about where these actually are, it's going to report this with an error of plus or minus 10 milliseconds, right? We don't actually know when we ask where this is. It could, well, I guess it's not plus or minus. In some sense, we know that it's plus or minus 5, I guess, technically, right? It's when we ask where this is, it could have been anywhere sort of in this zone. A 5 millisecond forwards, 5 milliseconds backwards in some sense. We don't know where it is because it updates so latently. So correlating our two buffers, we have up to 5 milliseconds of slop in there as well. That's just makes it even harder. So you see why this is so complicated. It really does make it pretty tricky for us to figure out how we could actually try, if we wanted to, how we could actually try to hit this thing. We look at where we are, we look at what the play cursor is, we just don't know. The play cursor is only updating every 10, so for all we know, the play cursor could be 10 milliseconds ahead or 5 milliseconds ahead or 5 milliseconds behind in terms of wall clock time. So we have to figure that every time we wake up, this is going to be this kind of nasty thing that shifts back and forth by 5 milliseconds. And 5 milliseconds is enough that we could end up, if we looked at where the right cursor is and we said, oh, it's inside, based on that estimate, what if that's wrong because of the 5 milliseconds? And it's going to jump forwards very soon, soon thereafter. We could assume that it's always a minimum bound and do it that way. I'm trying to think if there's any downside to doing that. I assume it's always conservative. So I think we're probably still okay. I think we're probably still okay. Yeah. So I guess what we can do is just use the play cursor to determine where we are in the buffer, right? So basically, here's our sound buffer. We basically wake up, we say, where is the play cursor in the sound buffer, right? We mark where that is. That's where we are in the play cursor, right? At this time. We then know we have a certain amount of time left to go, so that we map into samples. We say, okay, here is where the frame boundary would be in samples, right? We say it's this many samples ahead of the play cursor. We look at the right cursor and we say, where is the right cursor relative to that, right? That's stable no matter what, I guess, because, hey, it's a little late and whatever. We look at the right cursor. If the right cursor is behind that, then we're in this case. If the right cursor is ahead of that, then we're in the other case. I'm happy. I'm pretty happy with that. Basically, this is the same as a normal sound output loop, which would basically just be doing this, right? But we've now identified this other case where if we were given really low latency sound output, I think we now can actually literally hit our sound sync exactly. The more as the audio card converges to accurate, we will converge towards outputting sound that is right on that frame flip, like right on it, if that makes sense. I'm pretty happy about that. Maybe there's a mistake in our logic somewhere, but I'm pretty happy about what we just worked out. I wish we had a little thing that was like a little happiness flag. I feel like maybe the owl of shame, I don't know, maybe the owl of shame shouldn't be an owl of shame. Maybe we shouldn't reinforce our shame. Maybe we should reinforce our victories. I don't know, what do you think? Should it be an owl of victory or an owl of shame? Or do I just need to get two owls? I guess I'll leave that to the stream. And maybe even in the forums. We'll have to have a thread that's basically owl of shame or owl of victory. Which one do we want? And I don't know. Of course, we can't hold it up yet because we don't know if this actually works, and we have to go actually do it because there may be a hole in our logic. But I like this. So what I'm going to do is I'm going to write a little comment here down at the sound output code that sort of says how this works. And when we extract this out and clean it up a little bit, we're basically going to leave that comment in there, just something that says how this works. So, because that was pretty important. It took us a while to figure out, so I'd like to kind of just notate it so that it's very clear. How sound output computation works. So, what we're going to say is we're going to say, in the case, so when we wake up to write audio, basically we will look and see what the play cursor position is, and we will forecast ahead where we think the play cursor will be after sorry, we will forecast ahead where we think the play cursor will be on the next frame boundary, right? We will then look to see if the right cursor is before that. If it is, we will write up to the next frame boundary from the right cursor, and then one frame further, which should give us basically exactly what we want. We will write up to the next, so one frame boundary, if it's before the frame boundary, we write up to the frame boundary, and then one frame further, giving us perfect audio sync in the case of a card that has low enough latency, right? So basically, we will write, we will write up to, I don't know how to say this right. So we will look to see if the right cursor is before that. If it is, I guess we'll say the target fill level, or whatever, target fill position, is that frame boundary plus one frame, right? This gives us perfect audio sync in the case of a sound card that has low enough audio latency, right? If the right cursor is after the next frame boundary, then we assume we can never sync the audio perfectly. So we will write 1 frame's worth of audio plus a guard plus some number of guard samples. So, 1 millisecond or something determined to be safe, right? So we can actually say this is whatever this is. Maybe it's half the frame time. It's whatever we think the variability, of our frame computation is, right? So we could set that all the way up to 1 whole frame ahead if we were nervous, but basically that's really all we need to do. And this is the same. Basically, what we need to say, if the right cursor is before that, it's really before that by our safe amount, right? So we basically have a safe amount. We should sort of define this here. We will say we define a safety value that is the number of milliseconds or the number of samples we think our game update loop may vary by, right? And so however much that is. Let's say we assume that our game update can vary by, up to 2 milliseconds. Let's say up to 2 milliseconds or something like this. So we'll say that if the game update varies by up to 2 milliseconds, then when we wake up with the audio, we look and see if play cursor is, we look to see if the right cursor is before that by the safety value, or by at least our safety value. And if it is, the target fill position is the frame boundary plus 1 frame. This gives us perfect audio sync in case the card has low enough latency. If the right cursor is after that safety margin, then we assume we can never sync the audio perfectly, so we'll write 1 frame's worth of audio plus some number of guard samples. So this, I think, plus the safety margin's worth of guard samples. So basically this does exactly the thresholding that I set out to do initially, which is to say we always write 1 frame plus whatever the guard amount is in the case where we can't get audio sync to work right, because the card's too slow. If we magically were able to get some hardware that was fast enough, some really low latency hardware, then it would correctly do sort of the forward prediction to line it up with when we expect to flip, right? So that's, I'm pretty comfortable with that. How do you guys feel about that on the stream? How do we feel? I don't know. I don't know what you guys are doing out there exactly, but hopefully people are following that. But that's what we basically want to do. So what we do here is we take a look. We always have to basically write so you know what, we're gonna always look at we don't have to save, it's kind of nice, we don't have to save this stuff anymore for around the bend. We don't actually have to do that because we can actually, the last right cursor, last play cursor thing, we don't actually have to save anymore, so that's kind of nice. We can go down here and basically get rid of that and say that from now on we're actually just going to use this stuff, and we don't have to save sound as valid as well. We're pretty much good to go on that as well. So sound is valid. Can actually now be moved back down to here where we actually can do it. So sound is valid, doesn't have to loop. This is going to be nice. This is going to clean up a bunch of stuff. I'm going to leave this code in here for now because this is basically, let's see here, right cursor and play cursor. I'm going to actually leave this code in the debugging pass here so that we can actually, inside that internal thing, I still want to record those markers at this point because I think that's actually going to be useful. And so what I'm going to do is I'm just going to move the sound is valid stuff up to here. So sound is valid. We're actually going to go ahead and do that here. Maybe I still do want to actually keep it that sound is valid global now that I think about it, because we need to still handle the case where we're starting up. So I'm going to leave that. I'm going to leave that going. And so what we're going to do is I am going to do the get current position. I'm going to do that. Where is the OK thing? There it is. All right, go back a little. There it is. All right, so I'm going to go ahead and get that position like we wanted. I'm going to basically say, first of all, we've got a couple cases here. I don't actually know yet whether we need to maintain the sound is valid thing. I think we do, because we need to set where we're going to write to. So basically, if the sound isn't valid currently, we're going to assume that the place that we're going to write to is going to be roughly there. Now we have one little problem as well, which is that the game update and render is happening sort of after this. So we don't actually know, this is a bit of a rub in the plan. We only know the estimate for how long that's going to take. We don't actually know exactly how long that's going to take, but I guess that's okay, because we sort of know its expected time plus its variability. So that's the real tricky part here. Man, it is really complicated if you want to try and get real audio sync. This is really pretty darn tough if you get right down to it. Trying to manage these two clocks is pretty crazy. We're going to have to actually account for the fact that in order to ask the game to give us the audio for this frame, we need to know how many bytes to ask for, but in order to know how many bytes to ask for, we have to do it before we ask the game, so we don't know actually, like, we wanted to wake up and write the sound immediately, but we can't actually do that. I mean, we could, I suppose, actually do that and assume that the game update doesn't take as long as it's going to take for the right cursor to jump, but we don't actually know if that's going to be true or not. It could very easily jump. So that's a little bit tricky. That's a little bit tricky. That's going to complicate our computation. But all right, let's start out. We'll start out with it, and we'll keep on pushing through. All right. Okay, so we go ahead and get that current position. We take a look to see whether the sound is valid or not. If the sound is not valid, then basically we're going to probably going to defer that until after we actually do that. So that'll still probably happen here, so where we do our recheck. So basically what we need to do first is we need to determine how many samples we're going to actually ask the game for. So I see how we can probably do this. I I do. I think I see how we do this. We're going to have to do it a little bit weirder, but let's do it. Let's reverse this a little bit. So we're going to do it roughly exactly like we said here. We are about to fill the sound buffer. So we got the sound back from the game. So we're just going to go ahead and do that right in line here. So what we're going to do is we're going to get that current position, right? We're going to print this out there. Okay. So we're going to get that position. We're going to look at the play cursor and the write cursor. So we woke up there. We're going to ignore sound is valid for a minute because we're going to set that sound is valid. So we set that up here, and that's just a flag that we can use to know whether it's our first time through or not. So basically what we're going to do is, did I actually accidentally delete where is the running sample index update thing? I did. Yes, that was bad, Casey. Don't do that. Why did you delete that? Why did you delete that? Because that was code that we still wanted. I don't know why I deleted it. Probably just because I'm overzealous. All right. So what we want to do here is we're going to move this down, and I'm not going to delete that code. That code is good. It's code we actually want. So in here, in the case where that happens, there we go. And that's what we wanted to see happen. Now we've preserved the code that we actually still need. I don't know why I was feeling so overzealous there. All right. This is not going to be inside a sound valid loop. There we go. So in the case where we get it, we check to see if the sound is valid. If the sound is not valid, we're going to write from the right cursor. Obviously, that's the first place we have to write. That's where we need to start writing from. If our sound is valid, if we don't get it, then we're going to assume that the sound is not valid and restart the process, or just never write sound again. This basically means our buffer failed or something like that. So we look for the current position. If the sound is valid, we're going to start writing at the right cursor. Otherwise, we always write wherever we actually left off before. That's basically what we're going to do there. We're then going to say the byte to lock always has to be wherever we last wrote to, or right at the right cursor if we're writing for the first time, and that's still correct. Then our target cursor is the new thing that we're going to compute a little bit differently. Basically, what we're going to assume that it is, like I said before, is we've got two cases essentially. We've got these two cases to deal with. So basically, we need to do an if here, and we need to figure out that target cursor in two different ways, right? And the target cursor now, I believe this stuff can be moved inside this loop. It can be made to be direct, like this. I think so. So play cursor and right cursor still need to be out there, but everything else is fine. Good deal. So play cursor and right cursor get grabbed. That's all good. We're going to compute the byte to lock. That's relatively straightforward. So we do that. We can actually even do that directly in line here. So there we go. We'll compute the byte to lock that way. We then go ahead and try to compute the target cursor, and then we compute the bytes to write. So the target cursor has two cases. One is that we're just going to use the right cursor, the exact sort of thing we were doing before. The right cursor plus our safety, let's call this our safety sample bytes, right? So we're just going to get rid of that instead of sample count. I'm going to stop using samples anywhere I can, and then we'll start to simplify this code by just using bytes. Our target cursor is just going to be a wrapped version of basically the expected bytes per frame, and this is our safety bytes. There we go. Our expected bytes per frame plus our expected sound bytes per frame plus our safety bytes, right? So that's basically what we need to do there. And then this is in the case of a latent audio card. If audio card is latent, then we will do that. If it is not, then our target cursor is going to be equal to the expected frame boundary, right? Expected frame boundary byte plus plus the sound output just the expected sound bytes per frame. That's it, like that. So the right cursor just doesn't factor into it, basically. Yeah, I think that's it. Well, the right cursor, plus the sound is, that's it. That's all there is to it. I think that's really all there is to it. Yeah. I don't see anything wrong with that. We can move this out here, so we can say that the target cursor equals the target cursor mod the sound cursor bytes, so we know that it's always inside, and then we can just get rid of that and do this computation a little more cleanly in either case. So we're basically just doing this, right? Like that. I think that is correct. So now we just have to compute audio card is latent. So audio card is latent. That is going to be our assumption, certainly, because, well, most audio cards probably are, if that makes sense. So we're going to see if the audio card is latent by saying, what did we say up here? We basically said if the right cursor, let's say, if the right cursor plus the expected sound bytes per frame, right? If the right cursor plus the expected sound bytes per frame basically is safe right cursor, let's call this. Sorry, not the expected right cursor plus the safety bytes, right? That's where we know that that's accounting sort of for the jitter. If the safe right cursor, right, plus that, we need to kind of know what this expected frame boundary byte is. So we basically say if the safe right cursor is less than the expected frame boundary byte, right? Then we consider the audio card to not be latent. Make some sense? So in some sense, this is saying the audio card is latent if the safe right cursor is greater than or equal to that. Okay. So we're basically saying wherever we think the frame boundary is going to be, we basically, yeah, I mean, that's it, right? So really it's just computing this that we have to do. Okay, D-word, there we go. So basically we're just saying the safe right cursor is the right cursor plus whatever our safety byte margin is, which is how much variability we think there is in our output timing, right? Determining whether the audio card is latent is saying wherever that is, if that is after wherever we think our next flip will be, then we know that the audio card is not low latency enough for us to do perfect audio sync, right? So then we're going to say basically whatever that target cursor is just going to be computed based on either of those and then wrapped back into the buffer, and that's about it. So this is the only computation we actually have to do. What this actually is, whatever the expected frame boundary byte is basically the play cursor plus the expected bytes per frame. Now we have a problem here, which is again that the right cursor and the play cursor may have wrapped. So what we want to do is basically say what we want to do here is basically make sure that they aren't wrapped relative to each other. We're assuming that the right cursor and the play cursor are sort of in the same space. And so what we need to do is say if the expected frame boundary byte, we're essentially on the wrong side of whatever that safe right cursor is, right? Because, yeah, so we kind of need to take the play cursor and the right cursor and normalize them first. So I think what I'd like to do is just take that out of the equation because this is complicated enough already. So let's just say we have a mapped, our safe right cursor is going to map into the same place as the play cursor. Yeah, that's I guess what I'm going to say. So basically what I would say is the safe right cursor equals the right cursor. We're going to take safe right cursor and we're going to add the safety bytes in like this, so that I split those out excuse me, into two so I can make sure these were in the same place. So if the safe right cursor for some reason was behind the play cursor, then the safe right cursor is going to be normalized up to be ahead of it, right? So we assert here that the safe right cursor is always greater than or equal to the play cursor. All right, so that looks a bit better now to me. All right, so we're going to take the expected frame boundary byte. That's going to be the play cursor plus however many bytes we expect to output on a particular frame. That's going to be some kind of a value that we compute up above that's pretty rote. It's just going to be however much the milliseconds is multiplied out by the sound thing. So basically we've got that. We then check the safe right cursor is the right cursor. If it's behind the play cursor, which means it has wrapped, we're going to go ahead and normalize it so that it's ahead. We're not really normalize it, unwrap it so that it's always ahead of the play cursor so that we can do our computation properly. We take that safe right cursor, we assert that that it's always going to be ahead of it because that was our goal. We then add in the safety bytes. That is where we say it could possibly be. We look to see if the audio card is latent. If the audio card is latent, by saying, is that safe right cursor going to be before, I guess we could kind of reverse this. Audio card is low latency, might be a bit better. So we'll say if we can hit our thing, then we're gonna just reverse the sense of this test. So we're gonna say if the audio card is low latency, then we will go ahead and compute that right there. So okay, there we go. So that's how we determine this. That determines our latency. That's pretty good. We go through here. We say compute the target cursor by using just the frame boundary plus however many bytes we normally write per frame when we are low latency. When we are high latency, we basically just use that plus the safety margin, and that's the target. We write to the target here. We map the target back into the buffer properly, and then we go ahead and do the bytes to write. So yeah, pretty complicated computation, ladies and gentlemen. That is pretty darn complicated. So there we go. There we go. I guess that's really modulo the bugs. That's really what we wanted to do. So now we've got one more thing to deal with. Well, we got two more things to deal with, really. So the expected sound bytes per frame is not defined yet, right? We got to deal with that. So let's go ahead and deal with that. So we've got to define that in a second. And then we've got that safety bytes. We've got sound output safety bytes that we've got to deal with as well at some point. And then we've got, let's see, undeclared identifier for that. That's fine. Sound bytes per frame, safety bytes, still not a member. Last play cursor is not actually there, so we're going to actually have to do just play cursor and write cursor. So we'll get rid of that. Let's take a look here. Bytes to write, bytes do. So these are unfortunately, yeah, not known anymore. So is there a way I can do this? Byte to lock is there. There we go. Okay, so byte to lock, target cursor, bytes to write, play cursor, write cursor, audio latency bytes, audio latency seconds. So we're still outputting all of that, and that's good. Okay, so our problem here, besides defining these things, our problem here is basically that we still need to tell the game how many samples it should output, and that's kind of that basically gives us another audio latency problem, because where we want to actually do the write is right here, but the game doesn't actually, unfortunately doesn't actually, hasn't actually updated. If we were to put this before, in order to tell the game how many samples to write, then we would have to, we wouldn't actually have an accurate read on where the play cursor was going to be when we needed to fill. So this is what we actually want to do for our fill. And we can assume basically that the sound buffer here, we basically need that sound buffer to basically always be enough that we wouldn't underflow it here. And so what we can do there, I guess, is just kind of have a thing which says we're generally going to write enough. We want to make sure this bytes to write value never underflows is basically the problem. And so what is the maximum value that bytes to write could possibly be? I don't actually know. I guess it could be the expected frame boundary byte plus the expected sound bytes per frame. So in this case, it could actually be pretty high. Yeah. So if we move this before here, then we have another thing we've got to count on. Yeah, you can see how tricky this basically is, right? So what we want to do is we want to, if maybe, well, one thing we could do is we could then ask for the audio right here for the game and mix it on demand. And as long as we were able to keep that to within a millisecond or two, then that would be okay, potentially. But if it was going to be long, I don't know. So it's pretty tricky. It's pretty tricky. Should we do that? Should we not do that? Are we at risk there? I guess let's do it. I don't know. I'm feeling experimental today, so I say we just do it. So basically what's going to happen here is I'm going to say that we actually just go ahead and we get that sound straight out of here. So we go in here and we say, all right, what are we going to do? We're going to say internal void game get sound samples. So that's a call into the game, and we pass that everything except the graphics. The input don't come in, so we pass that the game memory, and we pass that the sound buffer, and basically we will say that the game just does its mix down right there, right into the buffer. So basically the game no longer gets the sound buffer at all, and so the game has to give us sound buffers on demand like this. So in here we will simply say let's go ahead and as soon as we know how many bytes to write, we will actually do the write right here, and that has to be low latency, which is the thing that makes me nervous about it, obviously. That's the reason that I was kind of like, oh, I don't know, this sounds dangerous. Well, you know, like I said, sometimes you just got to do stuff, and then you got to fight through it and see if there's something good on the other side. And sometimes there isn't, and it turned out to be bad. It was a mistake. And other times you come out with something really cool. And so sometimes you just got to do it and see. And so this is basically what we're doing here. Is we're just kind of fighting through it and going, can we get something cool out the other end? And maybe there's a few more refinements left that we'll have insights into and see. But let's take a look here. So basically we'll get the sound samples right here, and we will output them right here. The other thing that we could do, which is pretty interesting if we wanted to, is we could write directly into the sound buffer here now if we wanted to, because we could change to doing passing a ring buffer to the game. We don't really, I don't think, want to do that at this point, but that's what we would do. So, all right, we went in here and we did that. We now have our explanation in here. I might actually move this explanation kind of inside. So basically, this is the explanation of what's happening in here. And that looks relatively clean to me at the moment. So we get the get gigabit sound samples. But I'm going to put a note here. I'm going to say, at the moment, this has to be a very fast function. It cannot be, let's say, more than a millisecond or so, right? So that's going to be important to keep our sound latency down. All right. So basically, we can always account for more of that by buffering up, and maybe we could measure things here. I could say, to do Casey, reduce the pressure on this function's performance by measuring it or asking about it, etc. We could think about doing some stuff there to make that a little easier. But for now, let's actually say that that's the case. So compiling this, we now have to go through and fix. I left a bunch of stuff in there. So game update and render no longer takes the sound buffer. So that's got to happen. So we'll fix that in a second. We have the expected sound bytes per frame. We know what that is. That's basically just the game update hertz, which we had, right? We've got the sound output, the total secondary buffer size. Basically, we've got, let's see, samples per second. We've got the samples per second times the bytes per sample. Again, should probably, I'm going to go through and change some of those so we don't have to keep doing these multiplies. Divided by the game update hertz. That's how many sound bytes we expect per frame, right? Because we've got the bytes per sample coming out, the samples per second. That's going to be how many bytes per second, and then we're gonna go ahead and see how many per frame by dividing by the game update hertz. So that should be stable computation. Our safety bytes is something that we will define kind of at the top when we first do our sound output setup. So and that is basically sort of like what this latency sample count is. So basically what we have to say there is how much do we think? Well, I think we can safely probably say that the variability in our game time is probably not going to be more than half the game time, right? So our safety bytes is probably something like the samples per second times the bytes per sample divided by the game update hertz, divided by 2. I think that's a pretty safe estimate. It's probably more like going to be more than like more of a quarter or a third, I'd say, because in general I don't think we're going to have that much variability in how long the update takes. So basically I think we could probably do this a little bit lower. So to do basically actually compute this variance and see what the lowest reasonable value is. That makes sense. Kind of get that in there, take a look at it. And then I just got to add that to this thing here. Let's see, dword safety bytes. There we go. Warning treat as error, game update and render. Right, so basically now we have to go in here and split this out. If you remember, we decided we changed the definition of these functions. So we got to go in here and basically and basically split our functions into one that updates the sound and one that updates the game memory. So what we need to do here is we need to take this out, right, and get rid of that because we don't actually have that to do anymore. We're going to do this sound buffer output for the tone hertz. And basically what we need to do is we need to grab our game state. And so our game state is basically just, again, that permanent storage is how we access it. So let's go there, get that out from behind my head. Let's see. And we need to change this to be the proper function definition. It is this one now. So there we go. And go. There we go. Now, whew, man. We've got about 15 minutes before we would call this time for Q&A, probably. Sadly, I'm expecting that there's a ton of bugs in there because, man, that was a lot of code. So we still have a lot of work to do. We've still got a lot of work to do in the next 20 minutes or so. So let's run it just to see if we just full-on fail. Oh, well, let's turn off the infinite loop that we had there, first of all, and then see where we're at. At the very least, I am shocked that that still gives us clean sound output, ladies and gentlemen. And it actually feels fairly low latency, so we didn't introduce any weird bugs, which is kind of crazy, to say the least. That is kind of crazy. I am absolutely stunned that that worked the first time. I can only assume that there actually is a bug in there somewhere that we just don't find because we don't have testing for it yet. That is kind of crazy what we just did in an hour and 45 minutes of thinking and programming and not a single bug. That's wrong. Tom Forsyth says must be a bug, and I agree with him. There's no way that should have worked the first time. So basically what that means, we can just pretty much be sure that what that means is there's got to be a bug in there that we just aren't seeing because our test case is too simple. We don't know what we're not doing enough there. Yeah. Basically, somebody on the stream just says, I hate it when you compile and it works the first time. I could not agree more because it's just so suspicious. You want to fix some bugs in it so you can feel like you found them because you know they're there. And so now you just feel like there's bugs that are hiding. It's never like, oh, I did a good job, right? You never think that. So, yeah. So, well, there we go. So basically, let's take the 15 minutes, and I'm basically going to draw. I'm going to improve our drawing routine so we can kind of see a little bit more basically what's going on there, right? Let's go ahead and improve our drawing routine a little bit more. So what I want to do here is I want to, when we draw the sync display, what I want to do is start drawing some other things like when we have the play cursor and the right cursor, I want to draw where we actually did our write, and I want to pull out from there what just the current right cursor and play cursor are, so we can see those a little bit more cleanly, if that makes sense. Stretch time. Time to stretch, people. It's time to stretch. Yeah. Early morning coding. Here, well, afternoon. Afternoon coding. Not used to it for Handmade Hero. After Handmade Hero. Yeah, what are you going to do? All right. So that was crazy. And this is low-level stuff, too. I'm surprised that worked. I mean, we're essentially writing the game engine, like, low-level stuff here, the lowest of the low. So, yeah. That was crazy that worked the first time. I don't know what's going on. Usually you expect stuff to work the first time once you're a little higher up in the food chain. Things can work the first time because everything's fairly logical at that point and you've done all the finicky stuff and you've kind of baked it down into a language that's easy for you. But you wouldn't expect when you're doing the hardcore stuff, you don't expect it to work the first time. You don't. All right. So, well, what I want to do here is I want to start passing to the sync display. I want to say which marker is current. I wanted to say which is the current marker, right? So we can just highlight it. And so basically what I'm going to do is I'm going to say in this thing, if marker index equals current marker index, right? Then I'm going to use a highlighted color, current marker index, and if not, then not. So I'm going to do a thing for play color equals this, and right color equals that, sort of a thing. And then I'm going to set them equal here. So I believe the play cursor is our right cursor is our bright one, and the right cursor, right color, and is that. So right color and play color, that. And then I'm going to initialize those by default to something a little bit dimmer. Although I guess we don't, you know what I could do? I could just change the top and bottom actually. And so we basically just have two kind of rows going. That might be smarter. So let's say that this is pad y, and this is pad y plus line height, like that. Int line height equals maybe 32 or 64 or something like that. And so basically what we'll do is we'll just basically say, okay, that's the top and bottom, but in the case where the marker index, and whoops, we still want to do this because I think it's good to pull those out because we may want to change the color as well or something like that. So let's get that back in there. Boop, boop. And now we go ahead and take our top and bottom. We'll just go ahead and plus equal those to be, let's say, 2 times the line height or something like that. Or you know what? We'll do the line height plus the pad y. So we'll just move it down like that. Yeah. And so now we're not actually passing anything in there. So we got to come in and say, what is that current marker? And so the current marker is whatever this was before. So it's basically the debug. It's the previous one of the debug time marker index. So basically we come in here and we say the debug time markers. What is that value? It's not actually this one. It's this one, back one. But remember, we don't actually, if we subtract one from it, we may wrap. We don't actually care for right now. Note, this is wrong on the 0th index, or I should say current is wrong. But since we're just comparing to it, that's fine for now. So maybe I'll put to do in there, fix that in a second. Let's just see what that does. Yeah, so that's what we want. You can kind of see now we've got the historical ones are in there, but the other ones are in there as well. Let's go ahead and pause that for a second as well so we can take a look at it, because I can just click on there. Yeah, wow, so at least this confirms what we were measuring too in the diagram. You can see the difference between the play cursor and the right cursor is roughly the frame size, right? Exactly what we would think. Yeah. Yeah. All right. So that's fine. That's all well and good. Let's take a look here and see what else we got going. So what I want to do now is I also want to record with our markers. I want to record, I basically change what this records to record some additional stuff. This is where the play cursor and the right cursor were at the time of the actual, at the time of the flip. So this is the flip play cursor and the flip right cursor. But we basically want to also have the output play cursor and the output right cursor, right? Output right cursor. See where those were. And we want to do the output location. So that's like the output byte to lock and the output byte count. So basically this is the range we actually filled. So basically all I'm saying is back in here, so when we do this thing, when we do this, excuse me, when we do this this sort of save of the value, right? When we actually do this thing here where we actually save the value, I want to actually do this across. I want to do this multiple times. So basically, this debug time marker index thing, we're only going to increment it down at the end here, if that makes sense. Why did that do? No, because I just deleted it. There we go. So basically, at the end of this guy, we're going to do this. In fact, we could actually do this just to enforce the fact that it's being done at the very end. We'll do it down here in its own little block. So we're basically going to have a little thing that just increments that at the very end. So that way we can also write to this marker, the same audio marker for this frame, we can write to it up here. So basically, in the case if handmade internal, basically we will be able to write to the same marker that will be written to down there, and that way we can get a little more information. In fact, I guess I've already got a handmade internal in here as well. So there we go. We really probably don't need to do this again. We could decide to, but I don't think we really need to because we've already got this one up here. So we can do this. We could see how far it moved after the game gets sound samples, but you know, that's a separate thing. All right, so anyway, we're going to take a look at the marker here. We're going to go ahead and write all of these other values into it. We'll do the output play cursor. We'll do the output write cursor. And those are just the things that we just write. Output write cursor and the output play cursor. We will then do the output location, and that is the byte to lock, right? And the output byte count, and that is the bytes to write. And so now we've recorded that stuff properly, and all we have to do now is down in the other marker where we're writing these things. These are actually flip play cursor and flip write cursor, right? So what I'd like to do now, so we're recording all of that information, which is kind of handy. So here's the flip play cursor, here's the flip write cursor. Those are now there. Excuse me. Oops. Those are now there, and we should see exactly what we saw before now. There should be no change. Oops. Except there is. Oh, what did I do wrong there? Did I accidentally update that? Oh, yeah, awesome. That's good. When we actually wrap this guy, we need to actually do the wrap. Notice how asserts save you time. Basically, anytime you can, if you can assert the stuff that you know to be true, it definitely helps catch bugs. All right, so there we go. We're kind of in back in where we started land, and that's good. Everything looks about right, so that's happy. Okay. So now what we want to do is actually draw that actual information that we had, right? So we go into here to the thing, and this is the to-do we're working on right now, draw where we're writing the sound. So in the case where we have the current marker index, I'm going to draw some additional information, right? I'm going to go ahead and draw some additional stuff in the case where we have it. I want to draw all the rest of this stuff. So where do we actually have, what actual information do we have here in there? I've got the output play cursor. So that's coming up. Oops. Output play cursor. I've got the output write cursor, right? And I've got some more stuff here. I've got the output location, right? And then I've also got the output byte count. Now the output byte count is a little bit harder to draw. We can do it by basically doing this marker output location plus this marker output byte count, but we do have one problem with that, which is that could write off the end because remember, we're not actually checking this value. So what we should probably do here, because again, this is a circular write, so the number of bytes could wrap around the buffer, and we don't want to actually overdraw our screen. So what we could do here is just check our x. If our x is greater than or equal to 0, and our x is less than the back buffer width, right? Then we can actually draw. Otherwise, we won't draw, right? Makes sense? And in fact, we could even do that in the actual check here. We could do it right here just to make sure that basically anyone who draws this line is bounded there. Excuse me. Why do I still have a global back buffer typed in there? Don't do that. These should all be back buffer. There we go. So I'm going to go ahead and check that in there. I'm also going to do one other thing in there, which is we might as well also check the bottom and the top. Basically, if the top is less than or equal to 0, right? If the top is less than or equal to 0, the top can just be equal to 0. So that basically clips where we're writing to. And the same with the bottom. If the bottom is greater than or equal to the back buffer height, then we could clip the bottom and say bottom equals the back buffer height minus 1, right? And that would work. Oh, well, it's y less than bottom, so I guess we're okay by just saying it's equal to the height, like that. So if the bottom is, yeah, hopefully that makes some sense, right? Does that look reasonable to everyone? Hopefully that looks reasonable to everyone. I think that should be about right. I'm not actually sure because I have to think this through. So basically when we're passing the bottom, are we ever actually writing to the bottom? So let's say that the bottom, no, we're using less than. So if top and bottom were equal, we would not write anything. So if they were equal to height, we would not write anything. Top would have to be at least less than that. So we're okay. That's about right. So that's just, don't worry too much about that. I was just putting in some guards there against clipping off the screen. We're going to deal with that when we actually go write the renderer. I'll explain how these sorts of things work in great detail. So this is just some debug code to draw lines, and I wanted to make sure it wouldn't draw off the top, bottom, left, or right of the screen. So that's really all I was doing here. Anyway, so now I just need to go finish up this stuff, and let's see here. So basically, this marker needs to be snapped further up, so that's that. And then we also need some way of differentiating these guys. So we're going to say, basically, that I'm going to do this for now, which is kind of annoying, but I'm just going to basically keep moving those guys down as we go. And then, let's see, that should give us something that looks like this. Oh, but that was not correct at all. What? Oh, yeah. Well, so this assertion is no longer valid, unfortunately, because since I am actually using the output byte count thing that can wrap, basically this assertion, I did the clipping that assertion was guarding against up in here. So this assertion is really no longer valid. That assertion is going to assert, by definition when I do this addition, because that can wrap around the buffer. So that assertion is unfortunately no longer valid, which is too bad. We could assert some of the other buffer values in here, like we could do these other guys. Basically, these guys are all supposed to be correct, but we can't assert it every time we do that right, because it's actually kind of allowed to be wrong now. All of these things actually have to be less than the buffer size. Nobody is allowed to be less than, but once we add those two together, then that could be. So I'll just assert those here just to make sure everything's not wonky, but that should be correct. And this actually needs to, why was this not looking correct to me? So we should have, because we need one more, right? There we go. So, why are those two? So, okay, we got to change some stuff here. We've got two right colors on this one, play color. All right, so let's take a look at that. It'd be nice if we had labels and stuff, but let's take a look at that. So what do we have here? Basically, we're looking at that first one that we've got. And in fact, I guess while I do this, what I should do is bring this up in the debugger so we can see what the stuff is that we're actually looking at. All right. So what we're looking at here is we're looking at that first one is our actual play cursor, and our output right cursor is that first row below the baseline. So basically that is the white thing is where the play cursor was when we were going to output, and the red line is where the right cursor was when we were going to output. Then the location that we computed was kind of out. You can see where the white line is and the red line, that's where we were going to output. And then the flip location is basically is the bottom white line, is where the play cursor was when we flipped. So you can see that's actually working exactly like we hoped it would. You can even see that's pretty good. Like, look at what we did there. Basically, you can kind of see that very bottom one. I kind of need a way to pause this display. Let's do a way, because I need a way to move my mouse cursor around. So let's add a way to pause this display. I'm going to just go ahead and full on just throw in a way to pause the display here. So let's do that. Let's have a pause. Let's have some crazy global pause thing. So basically, you know, something like this. If handmade internal, there we go, p, then global pause equals not global pause, and we'll just have, this is just a full-on debug pause function. We'll probably want to make a pretty good one of these eventually. Global pause. And basically what global pause will do is it will just stop us from actually ever running the update. So basically, while global running, we'll basically say inside here, when we do this sort of stuff, do we want to pause the input? I'm not sure, probably not. So what we'll basically do is say if global pause, like this, if not global pause, then we'll do all this stuff, right? We'll actually make all this stuff happen. Otherwise, we won't. So get window dimension. We won't do the blit. We won't do any of this. This is none of this is going to happen. Yeah, and so our basically we have to not do any of this stuff. None of this stuff is allowed to happen at all. So we can't really do input either for the most part. Yeah, looks like we can't really do anything if we wanted to actually have it be a full pause. So let's see here. Let's do that. Let's do this. So the Win32 process messages still has to get called, so we can unpause basically. But yeah, that's sort of going to be buggy. We'll have to do a better implementation of that going forwards. Okay. Of course, I also need to actually only toggle that global pause when the key actually goes down. Global pause. So we need to do if is down, then global pause. There we go. All right. So we run that, and now we can pause. So basically what we've got here is this is where the current let's just verify this, right? So the first thing that we drew below the baseline, which is this thing, the first thing that we drew was just our output play cursor position and our output right cursor position. So that was where when we woke up, when we asked where the things were, that's where they were, right? We then computed where we were going to write to, and we basically said, well, we're going to write to right here. Oh, sorry, no, that's not actually correct. Is that actually correct? What's the next thing? The output location. Okay, yeah. So the next thing is the output location. So then we said, okay, the output location is going to be right here, and we're going to write this much. Then, when we actually came time to page flip, we page flipped here, and this is where the right cursor was going to be, although that's not super relevant. So this is where we page flipped. So this is our audio latency. Our audio latency is between these two things. And you can see that that's actually much less than a frame now, which is good. That's what we wanted. And I suspect that sometimes it'll even be better than that, depending on how things work out for us. It could even be a little bit less. Not actually entirely certain, but yeah. So that's pretty good. I think that's not bad. I'm relatively happy with that, especially because we're actually doing things so that we could do lower latency if we wanted to. Yeah, that's not awful. I'm not unhappy with that. I'm relatively happy with that. I'm relatively happy with that. All right. So that should be good. Blood Dragon, I just glanced at the chat because it's time to go to the question. It says initialize the global. Which global are you talking about? Global pause? This one? I thought we covered this. Global variables are initialized to 0 by default. And so pause is supposed to be false by default. But yeah. So someone was saying I missed an assertion for one of the things in here. Let's take a look. So output play cursor is asserted, right cursor is asserted, location, and then well, so we could assert the byte count because technically it does have to be less. It's not a position, but we could certainly, if it makes you more comfortable, we could certainly assert it because although we don't really care because we're wrapping that, we're clipping that value in the draw call. Although we don't necessarily super care, it is true that does have to be less than the secondary buffer size. That's certainly true. So that's good. All right. So I'm going to call that done for today. I don't, again, know that was rather surprising that all worked and does seem to be relatively robust as well. That could be deceiving, though. We haven't tested it thoroughly enough to really know. But yeah, I'm pretty happy with that. That was a good 2 hours of work, guys. That was a good 2 hours of work. What I'd like to do, ideally, if possible, is I would like to, at some point, go and find a low latency audio card and see if we can get it to the point where that frame display actually shows us that we're getting really low latency on the audio, because we want those two, on a really low latency card, we want those two lines to line up. So another thing that I might do is let's draw one more thing in our marker, which is basically the expected frame flip time. So basically the expected frame flip time, this thing, expected frame boundary byte. Let's draw that as well. So let's say expected frame boundary byte. So that's basically the expected flip cursor, right? Where we expect that to be when we actually computed the value, right? So that's to see whether our estimate lines up at all. So our expected flip play cursor is equal to where the play cursor is plus the expected sound bytes per frame. Okay, see, so that already tells me that that's sort of wrong now that I'm thinking about that. So we do have one incorrect thing here. It's actually that we forgot one part of the computation that I talked about. We forgot to do that the flip is not the whole frame times worth. It's just, it's only actually minus the time that's elapsed so far, right? Yeah. So we're actually not quite right. So let's draw this out, and we'll see that it's not quite right, and then we'll make the fix and put that in correctly. So all that does is add a little audio latency. So that's why we didn't see it as a bug, but we should be able to get that audio latency down. All right. So the expected frame boundary byte will also get written in here. Marker expected flip play cursor is that, and now we should see that this is not really that close. If we draw it, we should see that it's not really that close to the other line, right? So let's go in here and draw that. So when we do our play cursor and our output right cursor, we will also draw there, or I should say when we do this, let's do it here. So here's where we're writing to basically, yeah, okay, I'll do it here. So this is going to be expected flip color, right? And that's going to come out here, D word, expected flip color, oops, equals OX. Let's make that a nice cyan, shall we? Cyan would be good. So let's who doesn't love cyan? Oh, you know what we could do really purple, or we could do a yellow. Let's do a yellow. I like yellow. All right, so we're gonna do an expected flip color, and we're gonna draw. Ooh, did I just delete the? Yeah, it's expected flip cursor. Why did I do? What happened? I thought I typed this in. I'm just. You can tell I'm getting a little loopy here. Expected flip play cursor. Let's get that in there. There we go. So save. All right, so now we should see that is exactly wrong. And let's go ahead and assert that one as well. So the byte count. So that's expected flip play cursor. Like that. Let's take a look. So we should see. Oh, that's right. That's another one that also it's an added value. So that's actually allowed to be outside because that's normalized to outside. So there it is. Wow, it's real close though. Okay, so there's a case where it is not close, for example, right? But it is still really darn close, and I think that's just because our game, the milliseconds for our game update is so low that estimate is I guess going to be pretty close. That's within reason, but you can see that oftentimes if we're unlucky, and it's going to be a little further off there. So let's see if we can get that down a bit. Let's just see. So what I'm going to do is I'm just going to say, well, okay. So we have an ability to query the clock, right? And we're doing that often, right? So we're doing stuff where we have this sort of flip time. We take a look at what the flip time is right here. So we've got kind of the wall clock time here, and then we could if we wanted to also store whatever the actual time is right after the flip. So basically, right here, when we get this guy, right when we would call that query, let's just go ahead and have a thing here called flip wall clock, and we're just going to go ahead and get that, pull that out there, and store that, right? So let's just go ahead and do that. So we're going to do our flip wall clock is there, and we're going to go ahead and grab that every frame. So I've got that now. And that wall clock, flip wall clock, is just a large integer. So there you go. There's our flip wall clock. Boom. Our flip wall clock, which is going to be, basically a total nonsense value at first. But so the flip wall clock is basically right from when the flip occurred, and then we're going to time the time between that flip and where we are now, because that's what we said we were going to do. So we're going to go ahead and say, well, that flip wall clock, let's do that seconds elapsed here. There we go, when 30 get seconds elapsed. That flip wall clock, and wherever we actually are at the time when we do this computation for our expected, where is our expected here? Expected, here we go. So our expected sound bytes per frame is correct. But it's when we actually do the frame boundary byte, we're not going to use the entire expected sound bytes per frame, right? Because we're only using a part of them. So what we're going to do is right there, we're going to take a look. So essentially, right here when we do this check, we'll also do a thing where we basically say that we have an audio counter. The audio counter is going to be between here and the flip wall clock, right? I probably should call these either counter or wall clock correctly. So wall clock, audio wall clock. I should go through and change those. Wall clock. There we go. So basically what we end up with is the seconds so far. So the audio, the time between the beginning of the frame and so this is basically from begin to audio seconds. So that's what we've got. So now what we need to do is basically subtract that out of the expected frame time, and that is actually how many bytes forward we want to move this, right? So basically we've got sort of an expected thing here, and we're going to use only a part of it. So here we have expected bytes until flip, and that is essentially going to be the sound bytes per frame times whatever the actual proportion of a frame this actually is, right? And so, excuse me, whatever proportion of a frame we have here is what we need to multiply by, right? Because we've got the amount of time there toward the seconds per frame, our expected seconds per frame. That is the actual value that we need to multiply this by in order to get it. That's the coefficient that we need in order to get the amount of samples, the amount of bytes we actually think we're going to use. So the ratio of how much time we spent, actually that's not quite right. It's actually the expected seconds per frame minus this, right? It's the time left. So we have the expected seconds per frame minus how many audio seconds we've actually spent so far. It's how many seconds are left. So there's basically seconds left until flip is this. And so that's this value here, right? So the seconds left until we flip is however many seconds we expect to have per frame, and then minus the number of seconds that we actually already took. We go ahead and do the division to find out what percentage of the frame that is, and we multiply that by how many bytes we expect to have in the frame. So that's about it. So then we just have to have our expected seconds per frame value actually has to exist, but that's pretty easy to compute. When we take a look at our hertz, target seconds per frame. Oh, we've already got it. So that's what it is. It's just target seconds per frame. So it's target seconds per frame. So that's that. Target seconds per frame. That's that. And now let's see if I did that correctly. Let's pause. Let's see here. Still a bit off. Yeah, we're still getting that kind of, because what we want to see, right, is we want to see that value should be correlated with the bottom value, if I'm not mistaken. Let's double check. That's not we're not seeing what we hope to see. So let's go ahead here. So if we look at that, we should be correlating with this bottom value here. I think I was confused before, and I was looking at this one, which is not right. We're trying to correlate these two because this is our actual flip. We want the yellow to basically be correlated with that. And in fact, I guess what I should do is probably draw it all the way down to that level. Right? I mean, that would be sort of a better way to do it. Let me draw it essentially across all those lines. So this one, that way I don't make that mistake again. So we'll do it this way. Let's do that, and we'll just go ahead and do it. Oops, sorry. First top is what I meant. First top. So I'm just going to go ahead and draw this all the way down. There we go. Yeah. So what is going on here? We're still not where we want to be. That yellow value and that white value are not as correlated as I would like them to be, because that bottom white value, right? That bottom white value is where the play cursor is when we flip, right? That's what we were drawing, right? So this is our expected play cursor is that yellow line, right? Oh, okay. No, I'm right. So that bottom line, that very bottom is the actual flip cursor, right? So basically, we want the yellow line and that bottom white line. I'm not mistaken now. Those should actually be lining up as closely as possible. And they do a lot of the time, but it looks like we get into certain situations like this where they're pretty far away from each other. And I don't know if that's to be expected or not. I guess there is the fact that we can have that jitter up to 480 samples. So maybe what we should do is also draw in a 480 sample window to basically say, well, it could have moved by this much. Now, if it did, though, then it would be, yeah, well, okay. Let's draw that in and just see. So we knew that there was basically a 400, when we measured this card, we knew there was a 480 sample difference there. So I'm going to say, let's go ahead and draw that in. Let's do that in our play window, we'll call that. And we'll draw that in a lovely purple, is what we'll play window color. So I just want to see, basically, I want to see play window color. I want to see this plus 480 times the sound buffer, sound output bytes per sample. Right? I just want to see what that will look like. So looking at this a little more closely here, what we can see is basically that line is where the play cursor would be. This is where the play cursor was when we measured it for the flip. This is that 480 sample window, so that's the update granularity of the sound, and that's where we thought we were going to be. So generally, we are pretty darn close to being in between those two, but I feel like we should always be in between those two. And I don't like the fact that once in a while we get one that's a little further off than that. That feels like a bug to me. That just feels like it's not correct. Now maybe that's just because there's too much variability in our update, and we're not, so that's just natural. But I would have liked to have seen those converge a little bit more closely. So I suspect that maybe we're still a little bit buggy. Since this is not our final shipping code, I'm going to say we're probably okay to move on to something else for now. But this might be a kind of thing is when we have some extra time or when we're doing a bonus stream or something, to maybe come back, make some better, when we have more of a renderer and we can render the debug code a little more effectively, I would say let's come back to this because I'm not satisfied in the level of quality of this code yet. I think it still has a way to go. So I'm going to call that, but I'm going to call that done for now. I'm going to call that done for now because I don't want to rat hole on perfect audio output for too long. I want to keep it to within the stream. So let us go ahead and go to the Q&A now. It has been a long stream. That was like a 2.5-hour stream. That's a long one. And people are saying on the stream, write a full-on audio visualizer. Yes, well, eventually we will. So that's good. But let's go to Q&A now. Let's take a couple minutes of Q&A before we end the stream. Let's just stretch a little bit though. There we go. And I will switch over. Please make sure that you keep the questions to stuff we did today or in a previous day, and please make sure to put C-Muratory on each individual question so that I see them. Did you try the audio without OBS? I did. It did not change. So OBS did not seem to affect the audio output, which is what I would have expected because it's going through the kernel mixer, so it should be pretty free for the kernel mixer to hand that audio to OBS after it's done sending it out. So it should. I wouldn't have expected OBS to in a well-working system. It shouldn't, so I'm assuming that it was fine, and it was. Yeah. There was a lot of thinking today. A lot of thinking. A lot of thinking on the stream. Not seen any questions, though. Do we have no questions? Maybe everyone's too tired from such a long programming stint. And I can understand that. I can certainly understand that. It's been a lot of code. But hey, the good news is next week's, I think, almost exclusively fun stuff for the most part. So we did a lot of hard work. I of course, like this stuff, but I can appreciate the fact that other people might not. Let's take a look here. Is it inexpensive to query for the play cursor and the right cursor? Yeah, I think it's actually free. Is my thinking. The reason I say that is I don't think when you actually do that query, I don't think direct sound is actually doing any work. I think it's just returning you its internal values. And so I think what happens is direct sound updates those on its own time. So it's like occasionally resetting those values to whenever it pushes a new part of the buffer out or whatever, it updates those values. And then when you ask for them, I think you're just getting back whatever its values are at that time. So I don't actually think when you ask for it that it actually does any actual work. I could be wrong about that though. Audio seems to be the most complex part until now. Which will be the next more complicated thing? So I don't think we'll have anything as nearly as complicated as this audio output until we get to the rasterization of till we get to rendering non. So when we do the renderer, if we just have like a rectangle, if we're just drawing like rectangles on the screen that are filled with bitmaps, so we're just moving like bitmaps around the screen, that's not that complicated. It's pretty easy to understand. When we get to, because I would like to be able to support in our software renderer the ability to like deform and stretch things, like skeletal animation sort of thing. When we write the rasterizer for that, that's going to be crazy complicated. They're not that hard to write if you kind of just know everything already, but even when you do, there's a ton of debugging to do, and if you've never done it before, it's pretty darn crazy complicated. And especially if we go and optimize it, which we will for SIMD, it's going to be tough. So what we just did is the toughest thing we're going to do for probably quite some time. And the other stuff we're going to do, like loading a bitmap, is going to be a breeze compared to that. Drawing the bitmap to the screen, a breeze. Understanding gamma correction and stuff like that, maybe a little more complicated. Alpha blending, a little more complicated than that, but still way easier than what we just did. But then when we get to fully deformable rendering, that'd be the thing. Audio asserts are a pain when debugging other things. Change to log messages. Yes, I agree with that, Tom. And I wish we had a log. Are we asserting anything though now that would ever fail? I think the things we're asserting are now the only things we're asserting, Tom, are things that can't fail. Now, if they failed, you just got a full-on straight-up bug. I took out the assertion. I took out the only assertion that was asserting on something that was like an audio miss. So I think we've already got that covered. But I agree with you. You don't want to assert stuff like, oh, I missed the frame or whatever, because that happens, and then you're like, ah. If we had a buffer that played from start to finish, would it be a valid syncing method to manually set audio timer equals video timer? Yes, if I understand the question correctly. I'm not sure I understand exactly what you're asking. But are you basically saying, could we just use the audio's clock to determine when we flip? And I think you could. But the thing you have to remember is it's 480 sample granularity on this machine, right? So, just be aware that basically that's how granular it is, 10 milliseconds. So that's a pretty high window of error for your flip time. So you would basically get frame stutter, I think, if you actually tried to use that. Fully visualize waveforms and remove gradient, turn entire thing into massive audio visualizer. So we will probably do exactly that. When I said when we have better rendering code, because when we have better rendering code, it'll be trivial for us to render stuff like this. Like we had to go code all that stuff ourselves. And so I didn't want to go hog wild there because I'm like, we're just redoing work that we're doing later, right? But once we have some good rendering code in there, and we can just call it like you would in a higher level language where you've got libraries, we're going to build those things up, right? And then we're going to be able to program at a pretty high level not too long in the future. So I want to wait to do stuff that's like really good debug output with labels and stuff. I want to wait to do that until we actually have a renderer. If we had a buffer that played for finish, I did that one. We got a question. Could you please increase tone hertz to 512? My crappy laptop speakers can't output 256. I guess I don't see why not. We moved that into the platform non-specific code, right? So you're asking for this, right, something like this. That code's going to go away at some point. And put something. Better? Okay, let's take a look here. Turn. Will this audio system be able to handle music and sound, or will the game have to mux the audio for us? Well, the idea is that sound and music are not different. So all the sound, music, and sound effects all come out through this channel. So basically, the operating system only needs to provide us with a way to output audio on the left and right channel, and then the game just pushes everything through those channels. So the music will just get mixed directly in there along with all the sound effects, because music and sound effects aren't actually different as far as the game is concerned in terms of what it has to do. How will you make sure that you don't have regressions in some parts that are not that easy to spot right away? Well, you can't. I mean, it's part of the answer. You put as much debug visualization stuff in as you can, and you put in as much assertions in as you can. But one of the big problems with games is they're entirely user input driven. They're entirely based on stuff that comes back from the operating system. So you can't really unit test them. Like, you can't do a lot of testing of components because usually the component style stuff is the stuff that's easy to debug. And it's the cross-system, user input-based, like complex states of system stuff that fails. And so you really can't do regression testing on most of the hardest part of the stuff to test. So that's unfortunate. I'm sorry if I'm being slow, but I still don't truly understand why exactly the audio is jumping. I'm not sure what you mean by jumping. It just seems like we should be able to handle it more simply. I've been trying to put it together through the stream, but I'm just kind of lost. So I'm not sure what you mean by jumping. Could you be more specific, Starchy Pancakes, about... Starchy Pancakes is a great name. Why the audio is jumping. By this question, I mean the original problem, not the current iteration. And so I guess just tell me what you mean by jumping and original problem, so that I can be just type it in and we'll answer it there. Why is the pitch of the sound changes after the game has been running a little while? So actually, I don't think that actually happens. That's the controller. So I believe that the controller right now, this controller has a dead zone, as far as I can tell, and I haven't played with it yet, that's even bigger than the one specified by X input normally. And I noticed this when I was playing games too. It's really kind of annoying. But basically, I believe if we just took out the user input, so this was gone, right? We wouldn't hear that anymore. No, that's weird. That actually did change. What is going on there? I agree, that's a bit of a bug. Because I think our tone hertz should now be constant, right? So how are we actually getting a different sound output speed? Because that is even difficult for us to do. Because if we're always outputting it basically the exact same wave period, that seems pretty tricky. Now, to be fair, we're not actually accounting. One thing we could do is we could account for the fact that the sine loses its precision pretty quickly for our test value. So I should double check as well that that's not happening. Basically what happens is sign f, as this t sign goes up, I should guard against that happening. So the t sign value should basically just wrap every time it goes through 2 pi, right? So basically, if t sign is greater than 2 pi, right? T sign can go back down by that amount. Basically, just normalizing it to its period, if that made sense. But I don't think that should have been it. Maybe it was. Yeah, that's so for what it's worth, that's way sooner than I would have thought sine would have lost its floating point precision. But looks like that's it. Looks like it literally loses precision that quickly. And I guess that makes sense. Those numbers, when you think about it, the sine wave is oscillating many times inside a second. So that number is getting really huge, and you just blow out. That's kind of cool how fast that happened if you think about it. Basically, we've got a floating point number here, right? And the floating point number, let's do it this way. I'm basically gonna see if I can kind of isolate roughly when we hear that sound happen. I'm gonna go ahead and break into the game at the point where that happens. So game output sound. This is pretty cool. I'm pretty psyched that that was actually it. I wouldn't have expected that, but I wanted to check, and it turns out that was it. So what I'm going to do is I'm going to drop a breakpoint into the game, basically, as soon as I hear that sound. As soon as I hear the sound change, if that makes sense. I'm going to drop a breakpoint right there. Okay, so I heard the sound change a little bit. So let's take a look. Let's see what T sign is. So there we go. So basically what we have learned here is that when we get to 18,000, roughly 18,000, we have lost the precision necessary for the sign to still work properly. So I guess one question is, roughly where is that on the power of 2 spectrum, right? Where is that value? So if you think about what kind of power of 2 we need for that, that's somewhere around, 15 bits, let's say. Like if you, I don't know, where's the POW function? Scientific. What do we got here? Do we have square root? We do have square root. So let's see here. 2 to the 15th. Yeah, so that's somewhere around 2 to the 15th worth of bits in there. And then, so you figure if we have a 24-bit mantissa, right? So we have 24 bits worth of data in our sign, and we're using up, something like 15 of them. That gives us 9 bits of precision in our sine wave left. Am I doing that right? Let's say something like that at that point. And so 9 bits of precision in the sound wave. What would that actually be? So 2 to the 9th is 512. Oh, all right. So you can kind of see what the problem is. So basically, we're down to 512 steps in our sine wave, and I guess that is enough that we can actually hear the problem. So yeah, we just ran out of precision. There weren't enough bits in the floating point value to actually make that work. 512 steps, well, times 2 pi. So yeah, I don't know. That's kind of surprising that it happened so soon, but I guess you kind of got to figure there just aren't that many bits in a floating point value. They lose precision pretty quickly. So there we go. I'm going to go ahead and turn the user input back on and see if we also have a problem with the controller, because I think that may be true as well. No, that sounds pretty good. So that's pretty good. So it looks like maybe it was only just losing sign precision. Again, this is just test code, so we don't really have to care about that, but it is nice to get it out of there because, I mean, since it's test code, we want it to be consistent, and maybe like if we'd had another bug in the sound layer, that could have been masking it, and we could have been thinking, oh, there's just a bug in, you know, in the controller output or whatever, and you know, it's just getting rid of bugs, even if it's in code that doesn't matter at all, is still good because now at least we've reduced some variability there. Let's take a look. Sorry, I meant skipping. The original audio skipped when we moved the latency to be inside of 3 frames, I believe. Oh, okay. So the reason for that was basically just the way we were doing the computation was off of the play cursor. So we were kind of being a little too optimistic, right? Starchy pancakes, here is, I think, what you were asking. So basically what we were doing is we were looking at where the play cursor was. So we woke up and the play cursor is somewhere like here, right? Wherever it happens to be. And we were basically saying, okay, what we want to do is take the play cursor and take a look at where the next, I think what we were saying is something like, wherever the play cursor is, we're going to assume that the play cursor at the time of the flip, that's what we were doing. So the play cursor at the time of the flip, we were basically saying, let's go a frame ahead of that, right? Was what we wanted to do. And that's where we should actually write to. We should write to here in the buffer, right? So 1 frame ahead is what we would expect for it to be. And we're going to write 1 frame ahead of that, right? So it's basically 2 frames, right, is how much we would write ahead ideally. But we then knew that the right cursor actually was all the way out here when we started looking at it. So if the play cursor was even just a little bit off, then the right cursor would actually be here, and we would skip, right? Even if we were lined up properly. So what we had to do is write 1 full whole frame ahead of even the frame we were writing to ensure that by the time the play cursor got to the next one, the right cursor wasn't past the point that we had written to. Because if we'd written only to there, the right cursor would now be past it, and we'd get that gap. So it was really just because we wrote that code optimistically, assuming that the play cursor and the right cursor looked like that, but they actually look more like that, at least on this machine. If it's not too much of an issue, can we have line numbers on the side when you are coding so we can get a grip of where... well, so I don't know. Can we get them? I don't know if Emacs has that, but I could at least put them on in here because I think this has that, and I wouldn't mind having them here. I'm okay with that because I don't need the screen real estate for it. So let's see. Does the text editor have line numbers? Does it have line numbers? Yes. So there, at least then we'll have some line numbers in the debug. Okay, so let's see. Clemens Baum says, it's more likely to be the accumulation of a small value onto a larger value that is a numerical problem. Mantis is not lining up. Okay, so basically what they were saying is that we couldn't actually increment it by, well, that's basically the same thing. I mean, those are 2 sides of the same coin. Basically, the fact that we can't add a small value to it is the same as saying there isn't precision in it to record the size of the value that we actually need for the most part. But yeah, I agree that maybe if you could do the math in a way that was a little more amenable to it. Well, I'm not sure how you would actually do it. Yeah. I'm not sure how you'd actually reorganize that math without just dividing into where the sign would be. But if you were doing that, you wouldn't have it. You would never let it grow. So yeah, I'm not sure. All right. Well, my voice is about gone. So I think that is it for today. This has been a marathon session. I think we basically did a 3-hour session of Handmade Hero. But I said it was going to be long, and it was long. And I think we did some good work today. So thank you so much, everyone, for joining me. If you would like to get the source code, you can go to handmadehero.org and pre-order the game. It comes with the full source code updated every evening. You'll get a link in your email that you can use to download it, and it's divided by days, so you can always jump back and forth between any given day. Or if you want to use source code control, if you have a source code control system that you use, you can check it in every day. Even if you just start now, you can basically write a little script or something and unpack each individual one and create your own source code repository with it, basically. So you can go ahead and do that. If you have questions or want to discuss things, the news and forums link, that basically has all kinds of stuff. It has coding resources where people have ported the thing to other platforms. It's got a code discussion forum where you can ask questions. So it's pretty good. Basically, it's a good place to go just to talk to other people and find out stuff. Anyway, before I lose my voice, I will sign off now and say thanks so much for joining me for another episode of Handmade Hero. We will be back Monday night at 8 p.m. Pacific Standard Time, when we will start working on some more interesting stuff in terms of actually what goes on the screen. We'll start looking at how to actually get the game together. Now that we're pretty sure that we've got a reasonable platform layer, at least for prototyping, we'll probably do one more day of next week will mostly be about other stuff, but we'll probably do one more day of Win32 things. There's a couple fun things that I wanted to do. So we'll probably do a little bit more on the platform layer, since it took us 2 days to do the audio instead of one. So we'll basically go ahead and do one more day. But after that, we will be on to graphics, doing sort of graphic stuff on the screen and other sort of fun stuff that I think will be pretty interesting. So hopefully you will join us next week, 8 p.m. PST on Monday. Hope to see you all there. Yeah, thank you so much for joining me.